Long before the Earth took on the shape we recognize today, long before the Atlantic Ocean split the Americas from Europe, long before Asia rose above the Indian Ocean, and long before Africa settled into its present position, there existed a single massive landmass called Pangaea. Picture an age when virtually all the continents we know were fused together into one enormous supercontinent, stretching across endless deserts, towering mountains, winding rivers, and ancient forests. Dinosaurs roamed freely over this united terrain, while oceans lapped only at its far-flung edges. And deep beneath the surface, the restless tectonic forces were already shaping the planet's future. Why did Pangaea form in the first place? Why did it eventually fall apart? And what hidden clues might still lie within the Earth's crust where the pieces were once joined? To answer these questions, let's embark on a journey back to the prehistoric world. Imagine a time when a single, gigantic landmass dominated the globe, stretching almost from pole to pole. This supercontinent, known as Pangaea, began its story hundreds of millions of years ago, deep in Earth's ancient past. Its origins trace back to the late Paleozoic era, well before the first dinosaurs appeared. Pangaea did not appear overnight. It was the result of a slow but powerful movement that started around 335 million years ago during the Carboniferous period. At that time, the planet already hosted several large continental blocks. The two biggest were called Gondwana and Laurasia. Gondwana comprised the regions that would later become South America, Africa, Antarctica, Australia, and the Indian subcontinent. Laurasia gathered the lands that would eventually form North America, Europe, and most of Asia. For millions of years, these massive blocks drifted toward one another under the influence of forces hidden deep within the mantle. Gradually, like pieces of a gigantic mosaic, they converged, closing ancient oceans and merging into a single continent, Pangaea. The most complete configuration of Pangaea took shape during the Permian period and persisted until the early Triassic, roughly from 299 million to 200 million years ago. This was the golden age of the supercontinent, when almost all of Earth's land was concentrated in one place. Yet even such a colossal landmass could not endure forever. The same forces that had stitched the continents together eventually began to pull them apart. Around 100 to 75 million years ago, in the Middle Jurassic, cracks started to appear on Pangaea's surface. These fissures widened into deep faults and eventually gave rise to vast new oceans. Over time, the growing gaps split the single landmass into the smaller continents we recognize today: North and South America, Africa, Europe, Asia, Australia, and Antarctica, forming the familiar world we now inhabit. Why does Pangaea matter, even though it existed so long ago? Its legacy profoundly influences the planet's geology, climate, and the evolution of life itself. The ancient collisions and separations of its pieces set the stage for the distribution of rock formations, the patterns of ocean currents, and the pathways of biological dispersal that continue to shape Earth today. During the time when the supercontinent Pangaea was coming together, the planet's crust was intensely folded and fractured, producing some of the oldest and most impressive mountain ranges. In the eastern part of what is now North America, the Appalachians rose. In Europe, the Caledonian Chain formed, and in present-day Russia, the Urals appeared, all as a result of massive collisions between ancient land masses. These rugged peaks have stayed silent for eons, still bearing witness to the former might of Pangaea. When the giant continent began to split apart, an equally remarkable process took place. New oceans were born. As the continental blocks drifted away from each other, molten rock welled up from the mantle and spread across the gaps, laying down fresh ocean floor, especially in the region that would become the Atlantic. This seafloor building continues even today. The continents keep moving apart at a very slow pace, and the planet's map is constantly being reshaped. The climate of Pangaea was also unusual and harsh. Because the landmass was so vast, a large interior region lay far from any sea, away from the moderating influence of ocean breezes. Summers in the interior were blisteringly hot, while winters were bitterly cold. Much of the interior likely consisted of dry, dusty deserts. Encircling Pangaea was a massive ocean called Pangaea. With few small islands to interrupt currents, warm water could travel unimpeded around the equator, possibly intensifying the planet's heat.
This generated powerful and atypical weather patterns, perhaps including strong seasonal monsoons that dumped heavy rain on coastal areas while leaving the deep interior bone dry. One of the most fascinating aspects of Pangaea's story is its impact on living organisms. Because all the land was joined, animals could wander freely across the whole supercontinent. Fossils of creatures that once lived side by side on Pangaea are now found on continents separated by oceans. Take the small freshwater reptile Mesosaurus. Its remains have been discovered in both South America and Africa, even though those continents are today split by the Atlantic. Another example is Lystrosaurus, a pig-sized animal with traits of both reptiles and mammals. Its bones appear in distant places such as Africa, India, and Antarctica. These finds demonstrate that before the continents drifted apart, animals could populate the entire landmass. Plants show the same pattern. The prehistoric fern Glossopteris is a well-known case. Its fossils have turned up in South America, Africa, India, Australia, and elsewhere. Today, those regions host climates ranging from hot, humid jungles to icy tundra. Yet when they were part of Pangaea, they shared similar environments, allowing the fern to thrive almost everywhere. Pangaea also played a role in one of Earth's most devastating mass extinction events, the Permian-Triassic extinction, often called the Great Dying. This catastrophe occurred roughly 252 million years ago. During that crisis, about 96% of marine species vanished, and roughly 70% of terrestrial vertebrates disappeared. Scientists are still debating the exact cause. Some link the die-off to gigantic volcanic eruptions in Siberia, others to the extreme climate of the supercontinent, and many think both factors contributed. Even after Pangaea fell apart, its legacy continued to shape the planet's geological and biological history. When the continents began to drift apart, the planet formed fresh habitats. New mountains rose, coastlines reshaped, and fresh climate zones emerged. Life had to adjust, and new species evolved to meet the altered conditions, enriching the diversity of plants and animals. In this way, the ancient supercontinent Pangaea set the stage for much of what we see today: the placement of continents and mountain ranges, the flow of ocean currents, and the spread of flora and fauna across the globe. It reminds us that Earth is never static. Pangaea was not the first supercontinent, nor will it be the last. Earlier supercontinents such as Rodinia and Columbia existed, and in the far future, millions of years from now, the continents may converge again to form a new supercontinent. Exploring Pangaea is like stepping into a time machine. It helps us grasp not only the distant past, but also the dynamic, ever-changing nature of the world we call home. It shows how everything is linked to each other and to history, and how even the mightiest land masses are part of an endless cycle of transformation. For most of human history, people assumed the continents were fixed, immovable blocks of land. The notion that entire continents could slowly wander across the planet seemed absurd, and many scholars dismissed it outright.
Yet that once ridiculed idea became a cornerstone of geology. It is known as plate tectonics, and it explains some of Earth's most powerful and mysterious phenomena: earthquakes, volcanoes, towering mountain ranges, and the distribution of ancient plants and animals. The core idea of plate tectonics is that the Earth's outer shell, the lithosphere, is not a single, unbroken layer. Instead, it is broken into several massive, rigid pieces that fit together like a giant jigsaw puzzle. These plates are in constant motion, though they move so slowly that the movement is imperceptible, typically only a few centimeters each year, roughly the pace at which fingernails grow. Some plates carry continents, others make up the ocean floor. Where plates meet, three main types of interactions occur. At divergent boundaries, plates pull apart. As they separate, hot, molten rock from deep within the Earth rises to fill the gap, solidifying into new crust and forming extensive underwater mountain chains known as mid-ocean ridges. At convergent boundaries, plates collide. When two continental plates meet, they can thrust up massive mountain systems like the Himalayas. When an oceanic plate meets a continental plate, the denser oceanic slab often sinks beneath the lighter continental crust, creating deep-sea trenches, volcanic arcs, and powerful earthquakes. At transform boundaries, plates slide past one another. This sliding builds stress along faults, and the sudden release of that stress generates earthquakes, an example being the San Andreas Fault in California. What drives all this movement?
Deep beneath the surface, the mantle, a thick layer of hot, dense rock, is in constant motion. Imagine it as a gigantic pot of soup constantly simmering on a stove, its slow churn setting the entire planetary puzzle in motion. The heat coming from Earth's core makes the material there hotter and less dense, so it rises, while the cooler, heavier material sinks. This slow, circular movement of heat and rock is what we call a convection current, and over time it drags the material that sits above the tectonic plates along with it. The story of how we came to understand this isn't straightforward. It took a long, difficult road full of doubts before the idea finally took hold. It began with a daring German scientist named Alfred Wegener, who was born in 1880. He wasn't a geologist by training. His studies focused on weather and polar exploration. Yet his curious mind and careful observation led him to a remarkable insight. Around 1912, Wegener proposed a bold new concept known as continental drift. He noticed that the coastlines of South America and Africa fit together like pieces of a puzzle, which made him wonder whether those continents had once been joined. Although others had seen this similarity before, Wegener was the first to gather and organize convincing evidence from many scientific fields to support the notion that the continents actually move. One line of evidence came from fossils. He pointed out that fossils of a small freshwater reptile called Mesosaurus were found only in South America and Africa, despite the fact that the animal could not have crossed an ocean. This suggested that the two continents had once been connected. Wegener also highlighted fossils of land animals such as Lystrosaurus and Cynaegnathus, which appear on continents now separated by thousands of kilometers, including Africa, India, and Antarctica. Perhaps the most famous example was the fossil fern Glossopteris, discovered in South America, Africa, India, Australia, and even Antarctica. Since this plant could not have traveled across oceans, its wide distribution made sense only if those land masses had formed a single, giant continent. Wegener examined rocks and mountain ranges as well. He saw that the Appalachians in eastern North America line up almost perfectly with the mountain chains of Europe and North Africa, such as the Caledonian Mountains and the Atlas. These ridges consist of rocks of similar type and age, implying they were created during the same ancient events when the continents were still joined. He also turned to evidence of ancient climates. Wegener found signs that glaciers once covered parts of India, Africa, and Australia, places that are far too warm today for permanent ice. The only way to explain this was to assume those regions had once been situated near the South Pole. Conversely, he noted coal deposits that form in hot, swampy conditions in areas like Antarctica, which is now a frozen desert. This indicated that Antarctica had previously been much closer to the equator. Even though Wegener's theory was backed by a wide range of data, fossils, rock formations, and climate clues, many scientists of his era refused to accept it. The main problem was that he could not explain how the continents moved. Wegener suggested that the continents somehow broke through the ocean floor or were carried along by Earth's rotation and the Moon's attraction. However, physicists demonstrated that those forces are far too weak to shift such massive land masses. Without a clear mechanism, numerous specialists remained skeptical of his idea. Alfred Wegener wasn't a geologist, so many scientists treated him as an outsider and were reluctant to embrace his ideas. As a result, his hypothesis of continental drift stayed controversial for decades. It was a brilliant concept that was simply ahead of its time. The situation began to change in the 1950s and continued through the 1960s, when a new wave of scientific discoveries supplied the missing pieces that finally proved Wegener right. One of the most pivotal findings was the spreading of the ocean floor. Two researchers, American Harry Hess and Canadian Robert Dietz, proposed that new oceanic crust is constantly created at mid-ocean ridges. Molten rock rises from the mantle, solidifies, and then pushes the older crust outward, much like a conveyor belt. The strongest support for this idea came from the study of paleomagnetism, the ancient record of Earth's magnetic field preserved in rocks. Scientists discovered that iron-bearing minerals in the ocean floor align themselves with the magnetic field as they form. Because Earth's magnetic field flips polarity every few 100,000 to a few million years, the oceanic rocks display alternating bands of normal and reversed magnetization, first one direction, then the opposite, then the original again, and so on.
These magnetic stripes appear symmetrically on both sides of the mid-ocean ridges, forming a perfect mirror image. This symmetry demonstrated that new crust was being added at the ridge and then spreading away in opposite directions. Later, deep-sea drilling confirmed the pattern. The farther a rock sample lay from a ridge, the older it was, exactly as the seafloor spreading model predicted. Along with the discovery of seafloor spreading, modern science gained powerful tools that offered clear, undeniable evidence of continental movement. The Global Positioning System, which relies on a network of satellites orbiting high above Earth, allows researchers to measure the motion of massive tectonic plates with astonishing precision, down to a few millimeters per year. By placing GPS receivers at various locations around the world, on different continents and even remote islands, scientists can track how these plates shift over time. The movements are extremely slow, but they accumulate, and the data now show the drift of continents in real time, exactly as the theory of plate tectonics predicts. Such precise measurements leave no room for doubt. They confirm beyond question that Earth's crust is indeed moving. The clear, space-based evidence silenced the last skeptics who once mocked the idea. GPS isn't the only line of proof. Since Wegener's era, advances in rock and mountain research have provided additional confirmation. Modern dating techniques enable geologists to determine the ages of rock layers with great accuracy. By comparing formations on one continent with matching formations on another, often across an ocean, scientists find striking coincidences that support Wegener's original observations. Mountain ranges on different continents exhibit identical patterns of folds, bends, and large fractures called faults, which clearly resulted from ancient collisions of massive land masses. These geological fingerprints further validate the concept of continental drift that Wegener first proposed. Long ago, the continents formed a single landmass, and later the moving plates pushed against one another. When scientists map where volcanoes erupt and where earthquakes occur, they see that these dangerous events are not scattered at random. They cluster tightly along the edges of tectonic plates, exactly what we would expect if the slabs of the Earth were sliding and colliding. Even the ocean holds clues to this story.
By drilling deep into the sea floor, researchers can bring up rock samples that reveal the age and origin of the ocean crust. Those findings line up perfectly with the ideas of plate tectonics. But the evidence doesn't stop there. Today, geologists use seismic tomography, a technique that studies how earthquake waves travel through the Earth. The result is a giant, three-dimensional X-ray picture of the planet. These images show streams of hot rock rising from deep within, and colder, denser slabs sinking down into the mantle. The pattern reveals a slow circulation of material called mantle convection, which acts like a hidden engine that gradually moves the surface plates. The path from Alfred Wegener's once mocked notion of drifting continents in the early 20th century to the widely accepted theory of plate tectonics reads like one of science's most inspiring tales. It demonstrates how convincing evidence can accumulate over time, eventually incorporating doubt and resistance. It also reminds us how crucial it is to look at a problem from many angles, blending geology, physics, chemistry, and even space technology. Today, plate tectonics is more than a clever hypothesis. It is the foundation of our understanding of how the planet's surface changes. It explains not only the past arrangement of continents, but also gives us clues about their future. More than 300 million years ago, the ancient supercontinent Pangaea came together, only to break apart later, carving out the continents, the oceans, and even influencing the roots of life's evolution on Earth. When we talk about Earth's deep past, times so remote they are hard to imagine by today's standards, one name dominates the discussion: Pangaea. This massive land body is the best known of all supercontinents. It represents the last moment when most of today's continents were joined, and its subsequent breakup fashioned the modern world map we recognize. To truly grasp Pangaea, however, we must look even farther back, before its formation. Pangaea was not the first supercontinent, nor will it be the last. The planet has undergone many cycles in which continents gradually linked into a single, giant block, only to fragment again after millions of years. This repeating pattern is called the supercontinent cycle. It drives the slow mixing and movement of rocks deep beneath the surface in a layer known as the mantle. The grand cycle of supercontinent assembly and breakup has been occurring for billions of years. Each turn leaves its imprint in rocks, mountain ranges, and the magnetic signature of the Earth's crust. By reading these clues, scientists explore the planet's internal processes and piece together its long, eventful history. The story of the ancient supercontinents that preceded Pangaea, such as the land masses sometimes referred to as Nuna, Rodinia, or Columbia, offers a vivid picture of how the Earth changed, how its surface reshaped itself, and how life responded to those massive shifts. Imagine traveling back to a time when life was just getting started and the air we breathe today had not yet formed. Our journey begins in the Neo-Archean era, a span that lasted roughly from 2,700,000,000 to 2,500,000,000 years ago. It was during this interval that the supercontinent Kennerland came together. Kennerland ranks among the oldest supercontinents known to science, and its existence is backed by convincing geological evidence. Picture a world very different from our own. The sun shone dimmer, the atmosphere contained little or no oxygen, and any living organisms that existed were simple, microscopic forms. Yet beneath the surface, powerful forces were already at work, moving the planet's crust and shifting tectonic plates. Kennerland did not arise from the continents we recognize today. Instead, it assembled from a collection of smaller land blocks, often called protocontinents, and from ancient, stable pieces of craton rock. These cratons are some of the most ancient foundations of today's continents. The most important cratons that made up Kennerland included the Baltic Shield, which now forms part of Scandinavia and Eastern Europe, a craton that underlies much of modern North America, and another that lies beneath Western Australia. No single fragment of Kennerland survives on the surface today. Scientists have reconstructed its outline by matching very old fragments of rock from different continents and noticing that they once fit together. By examining the magnetic signatures locked within those rocks, a kind of ancient compass record, researchers could demonstrate that these distant regions had once been joined in a specific arrangement. They also compared the ages of rocks, the structures of ancient mountain belts, and the distribution of mineral deposits across the various cratons.
The assembly of Kennerland marked a major turning point in Earth's history. For the first time, large expanses of stable continental crust were united into a single, massive landmass. Before this, the planet's crust was probably thinner, hotter, and more fragmented, allowing tectonic processes to operate much more rapidly. Kennerland shows that, even billions of years ago, the Earth was already shifting toward a slower, more orderly system of plate movement, much like the pattern we observe today. Like every supercontinent, Kennerland's reign eventually ended. Its breakup likely began around 2,500 million years ago. Scientists think that rising columns of hot rock, known as mantle plumes, pushed up from deep within the Earth, pressing against the base of the supercontinent. This pressure caused the landmass to stretch, crack, and finally split apart. The fragmentation was accompanied by extensive volcanic eruptions that flooded vast areas with lava, creating what geologists call large igneous provinces. As Kennerland fell apart, its constituent cratons drifted away from one another, and new oceans opened between them. The disintegration of Kennerland provides a clear example that the cycle of supercontinents began long before recent geological times and has continued throughout the planet's long narrative. Studying this ancient supercontinent lets us peer into the era when the early continental crust first formed and stabilized. It also demonstrates how massive volcanic events that generate large igneous provinces can play a pivotal role in tearing continents apart. We see the same pattern repeated in later supercontinent cycles. Let us jump ahead to the Paleoproterozoic era, which lasted roughly from 2,800 million to 2,500 million years ago. After the breakup of the ancient continent Kennerland, its fragments did not stay isolated for long. Over hundreds of millions of years, they drifted back together, eventually forming a new, even larger supercontinent called Columbia, also known as Nuna. Columbia was far more extensive and complex than its predecessor. It emerged as a result of collisions among many old cratons and younger terrains. Imagine modern continents slowly grinding into one another. The forces involved raised enormous mountain ranges, some of which would dwarf anything we see today.
The most important components of Columbia included Laurentia, which later became the core of North America, the Baltic region, encompassing parts of Scandinavia and Eastern Europe, as well as Siberia, northern China, Western Africa, and a portion of Australia. Geologists have gathered stronger evidence for Columbia's existence than for Kenneland, identifying extensive belts of ancient mountains, so-called orogenic belts, created by the continent's assembly. A classic example is the Trans-Hudson Orogen, a vast zone of deformed rocks that stretches across central Canada and the northern United States. In addition to these collision zones, scientists have found traces of anerogenic magmatism, volcanic activity that occurred without accompanying mountain building, typically during quieter intervals between continental amalgamations. Columbia, however, did not endure indefinitely. Its breakup began around 1,500,000,000 years ago. As before, the disintegration was gradual. Rifting split the landmass, and new ocean basins opened in the gaps. The story of Columbia is crucial for understanding the evolution of Earth's tectonic system. It demonstrates that plate tectonics became increasingly vigorous and began to operate much as it does today. The formation and later fragmentation of Columbia were linked not only to the development of mountains and rocks, but also to major atmospheric and biological changes. The Great Oxidation Event, during which atmospheric oxygen levels rose markedly, had already taken place before Columbia formed. Yet the later phases of Columbia's history may have altered nutrient cycles in the oceans, fostering the diversification of early complex cells known as eukaryotes. Because relatively few new life forms appear during this interval, the time of Columbia's existence is sometimes dubbed the Boring Billion. Nonetheless, this prolonged tectonic stability illustrates how a supercontinent can shape the trajectory of life itself. Our next stop takes us further back, well before the age of dinosaurs, into the Neoproterozoic era, which spanned roughly from 1,500,000,000 to 750 million years ago. It was during this time that the ancient supercontinent Rodinia assembled. If the name Pangaea is familiar to most people as a hallmark of Earth's continental history, Rodinia can be thought of as its mysterious and even more powerful predecessor.
Though less celebrated, Rodinia's story is no less dramatic, perhaps even more so, than that of Pangaea. When Rodinia began to fragment, the planet experienced some of the most extreme climatic events in its history, including a period when ice may have covered almost the entire globe. Scientists refer to this episode as Snowball Earth. Shortly after this global glaciation, the first large and complex life forms appeared, setting the stage for the later explosion of biodiversity. The name Rodinia comes from the Russian word Rodina, meaning homeland, and this ancient continent truly was massive. Its core, Laurentia, later became the geological heart of what we now call North America. But this supercontinent did not appear overnight. Its formation took millions of years and was driven by a huge orogenic event known as the Grenville orogeny. This global mountain-building episode unfolded roughly between 1,300,000,000 and 1 billion years ago. During that interval, several older land masses, including fragments of today's South America, Africa, Australia, India, and Antarctica, slowly drifted together, converging around Laurentia. The collisions crumpled the crust and raised enormous mountain ranges. Although those peaks have long since been worn away by erosion, their deep roots persist in rocks scattered across different continents, showing that they once formed a single landmass. How do we know Rodinia ever existed? Geologists have gathered evidence from many parts of the world. paleomagnetic measurements reveal the positions of rocks at the time they formed, and similar rock types and structures appear on widely separated continents. For example, Grenville Age rocks in the eastern United States line up with rocks found in places such as Scandinavia, the British Isles, and even Antarctica. All of these clues point to a time when these lands were joined as part of Rodinia. The story, however, does not end with the supercontinent's assembly. Its breakup began about 750 million years ago and continued for several hundred million years, a process that was both dramatic and consequential. Scientists think that as Rodinia fragmented, mantle plumes, huge columns of superheated rock, rose toward the surface. This activity created new coastlines and shallow seas, while exposed land areas weathered chemically, drawing carbon dioxide out of the atmosphere. With less greenhouse gas to trap heat, the climate cooled sharply.
Volcanic eruptions that accompanied the breakup could temporarily boost warming, but they could not stop the ensuing deep glaciation. In the end, ice may have covered almost the entire planet. That icy episode set the stage for a new phase of evolution. Researchers suggest that the harsh, frozen conditions forced life to explore new, more complex forms. Soon after, the first sizable multicultural organisms known as the Ediacaran biota appeared. This evolutionary leap paved the way for the Cambrian explosion, a period of astonishing biological diversity. Thus, the rise and fall of Rodinia not only reshaped the planet's surface, but also steered the direction of life's development. Rodinia was not the only supercontinent to leave its mark. Earlier, two even older supercontinents, Kennerland and Columbia, had existed. Together, these three supercontinents form chapters of a much larger narrative called the supercontinent cycle. According to this concept, continents are not permanent fixtures. They slowly converge into gigantic land masses and then break apart again. Each cycle spans roughly 300 to 500 million years, a timescale almost unimaginable, yet fundamental to the dynamics of our planet. Two main models currently describe how supercontinents form, each offering a different perspective on the ever-changing arrangement of Earth's land. According to the introversion hypothesis, a new supercontinent forms when the internal oceans left behind by a previous breakup close up. The extroversion hypothesis tells a similar story, but with the continents drifting around the globe and meeting on the opposite side, sealing the external oceans. No matter which model is preferred, the overall sequence stays the same. Land masses join together, trap heat beneath them, eventually fracture, and the resulting fragments drift until they collide again, beginning a fresh cycle. This cycle does far more than redraw the outlines of the continents. It plays a major part in regulating Earth's climate, shaping sea level, steering ocean currents, and even guiding the evolution of life. When the continents reunite, the interior of the resulting supercontinent tends to become hot and arid. Because it lies far from the seas, oceanic currents are either blocked or forced to change direction, and the distribution of warm water across the planet is altered, which can trigger profound climatic shift. The planet's reflectivity also changes. The surface albedo, how much sunlight is reflected versus absorbed, depends on the balance between ice and land. A higher proportion of ice reflects more sunlight, while more land absorbs it. The supercontinent cycle also leaves its imprint on the carbon cycle. During the breakup of the supercontinent, volcanic activity intensifies, releasing large amounts of carbon dioxide into the atmosphere and potentially warming the globe. At the same time, newly exposed land undergoes weathering, a process that draws carbon dioxide out of the air and can lead to cooling, even to the extreme snowball Earth conditions recorded in the geological record. When continents pull apart,
mid-ocean ridges expand, displacing water and causing sea level to rise. Conversely, as continents converge again, ridge growth slows and sea level falls. Life follows the rhythm of this tectonic dance. The coming together or drifting apart of land masses creates fresh habitats while destroying old ones, a dynamic that can produce mass extinctions as well as bursts of evolutionary innovation. Shallow seas that appear during rifting provide ideal environments for marine organisms, boosting their diversity and abundance. The breakup of the supercontinent Rodinia illustrates how the cycle also determines where valuable mineral deposits end up. Important ore bodies form either under the immense pressure generated during continental collisions or when magma ascends during periods of rifting. Looking at Earth's deep history, each ancient supercontinent teaches a distinct lesson. Kennerland records the earliest stage, when the planet's crust was still finding stability. Columbia shows how the processes grew larger and more intricate, laying the groundwork for the modern system of tectonic plates. Rodinia, perhaps the most dramatic of all, demonstrates how the Earth's internal forces can reshape the surface and influence life itself. The story of Pangaea, the massive supercontinent that once gathered almost all of Earth's land, is not merely a tale of rocks and tectonic slabs. It is a captivating chapter in the planet's biological history. Pangaea did not appear overnight. Its formation was the result of a long, dramatic journey that spanned hundreds of millions of years.
To trace how this great landmass came into being, one must travel back to the Paleozoic era, which began roughly 541 million years ago and ended around 252 million years ago. That era, often called the Age of Ancient Life, was a time of astonishing change. Life surged forward, the climate shifted dramatically, and the continents began to wander, crash together, and reshape the planet's face. Tiny pieces of land took part in a slow, grand dance, inching closer until they finally collided and forged a massive continent. At that moment, life made a bold leap, from simple sea dwellers to complex plants and animals that learned to live on dry ground. Enormous forests sprouted, strange marine creatures vanished, and reptiles started their rise to dominance as the continents moved like pieces of a giant mosaic. When this era began, Earth's surface looked completely unlike today. The land was broken into many small fragments, the leftovers of the ancient supercontinent Rodinia, which had already split apart. Among those fragments, two huge landmasses stood out, the future supercontinents Gondwana and Laurasia. By the start of the Paleozoic period, Gondwana already existed as a supercontinent. It had formed earlier in the Neo-Proterozoic from pieces of Rodinia. Gondwana was vast, and most of what later became Paleozoa remained the largest block on the planet. It comprised the future territories of South America, Africa, Antarctica, Australia, India, Madagascar, the Arabian Peninsula, and even parts of modern-day Florida and southern China. Around 541 million years ago, at the dawn of the Paleozoic Age, Gondwana lay mainly in the southern hemisphere, with a large portion hugging the South Pole. Imagine this enormous landmass drifting northward for millions of years, like a colossal ship sailing across the globe. Its continual motion triggered huge changes. As Gondwana moved, different regions passed through a variety of climate belts. During the Ordovician and later the Carboniferous, Gondwana endured long spells of glaciation, with vast areas blanketed in ice. We know this from deep glacial scratches and shading discovered in cool places such as India and Africa. Those icy marks clearly show Gondwana's ancient trek near the pole. When the landmass shifted toward warmer latitudes, its interior became increasingly dry, turning into desert-like terrain. Meanwhile, the margins, coastlines, and zones with milder climates hosted rich and thriving ecosystems. One of the strongest pieces of evidence for Gondwana's past comes from plants. The fern-like Glossopteris spread across the supercontinent, and its fossils have been found on several modern continents, confirming that those lands were once joined. Gondwana did more than shape life. It altered ocean currents and wind patterns, forged the global climate, and decided where rain would fall and where drought would grip the earth. While Gondwana ruled the southern half, the northern hemisphere of the early Paleozoic world resembled a patchwork of smaller blocks. These included Laurentia, the future core of North America and Greenland, Baltic, the area of present-day Scandinavia and parts of Eastern Europe, Siberia, and Avalonia, which comprised regions east of North America as well as Britain and Ireland. Unlike the united, massive Gondwana, those northern fragments were scattered and drifted each in its own direction. Over many ages, the continents began to drift towards one another, slowly colliding and eventually merging into a single, immense landmass. This gradual joining took place later in the Paleozoic era and was accompanied by dramatic geological upheavals, massive continental collisions that reshaped the planet forever. As the land masses approached each other, they passed through a variety of climatic zones, each hosting distinctive plants and animals that bore little resemblance to the life forms that inhabited Gondwana. These biological differences reveal how isolated the continents had been until the assembly of Pangaea allowed northern and southern species to intermingle. The entire Paleozoic episode can be imagined as a grand, slow-motion dance, with the continents acting as enormous dancers steadily moving towards a final embrace. That climax was the formation of Pangaea, but it did not result from a single impact. Rather, it unfolded through a series of spectacular events. One of the earliest major episodes was the Caledonian orogeny, which dominated the Silurian and Devonian periods, roughly from 440 million to 390 million years ago. During this interval, the ancient continents of Laurentia, Baltica, and Avalonia drifted closer together. Between them lay the primordial ocean called the Iapetus, which gradually narrowed as the continents converged. When the land masses finally collided, they thrust up towering mountain ranges. The remnants of those ancient peaks are still visible today in the Appalachians of eastern North America, the Scottish Highlands, the Scandinavian mountains, and parts of Greenland. This collision gave rise to a new northern supercontinent, often referred to as Euro-America or Laurasia. An essential component of the Caledonian episode was the Akkadian orogeny, during which Avalonia collided directly with Laurentia, building additional mountains and more tightly binding the northern continents. The last and most dramatic convergence occurred during the Carboniferous and Permian periods, approximately from 320 million to 250 million years ago. At this time, the two gigantic blocks, Gondwana to the south and Laurasia to the north, finally met on a planetary scale. This phase is marked by two powerful mountain-building events, the Alleghanian and the Variscan, also called the Hercynian orogenies. The Alleghanian orogeny resulted from the colossal collision of Africa, then part of Gondwana, with North America, a component of Laurasia. This mighty impact raised the Appalachian Mountains, whose rugged outlines still dominate the landscape today. Simultaneously, on the opposite side of the assembling supercontinent, other folding events took place. Africa and smaller continental fragments slammed into what is now Europe, spawning the mountain systems of Central Asia, Southern Europe,
and the early forms of the Alps, the Pyrenees, and the Urals. These enormous collisions did more than create mountains. They reshaped the Earth's crust, triggered intense volcanic activity, and altered the planet's overall structure. All of these events, stacked one upon another like layers of a gigantic geological pie, eventually welded together all the major land masses into a single, colossal continent. This supercontinent stretched from the northern pole to the southern pole and was encircled by an immense global ocean, often called Pangaea. The Earth's continents, each hundreds of millions of years old, have drifted slowly and intermittently linked together, while life on the planet has undergone some of the most dramatic and striking transformations in its history. This sweeping chapter is known as the Paleozoic era, covering the span from about 541 million to 252 million years ago.
It was not merely an era of moving land masses. It was a time of profound geological and biological change. Life blossomed and spread rapidly, eventually reaching the land and confronting some of the most devastating extinction events recorded in Earth's history. We begin with the Cambrian period, which started about 541 million years ago with the remarkable Cambrian explosion. During this interval, the seas were brimming with new life forms. Almost every major animal group that we recognize today, those with spines, shells, or limbs, appeared in the fossil record within a geologically brief span. Yet this burst of diversity remained confined to the oceans. Life had not yet colonized the land. The shallow waters of newly exposed continental shelves, created after the breakup of the ancient supercontinent Rodinia, were rich in nutrients and provided ideal cradles for this flourishing marine life. The next interval, the Ordovician, lasted from roughly 485 to 443 million years ago. Oceanic life continued to diversify, and the first vertebrates, early fish, appeared. By the close of this period, simple non-vascular plants began to establish themselves on land. Though modest in size, their emergence marked a pivotal turning point for terrestrial ecosystems. The Ordovician ended in a catastrophic mass extinction, likely triggered by the massive southern drift of the continent Gondwana across the South Pole. This movement induced a glaciation episode. Glaciers expanded, sea levels fell, and numerous marine species vanished. Following this, the Silurian period spanned from about 443 to 419 million years ago. The seas remained teeming with life, and jawed fish emerged, a major evolutionary advancement. Meanwhile, plants continued their terrestrial expansion, developing vascular systems that could transport water and nutrients, enabling them to grow taller. Land animals also made their debut, with small arthropods such as centipedes and scorpions venturing onto moist ground. Shifts in continental positions altered ocean currents and forged new habitats, further driving steward progress. The Devonian period, lasting from 419 to 359 million years ago, is often called the Age of Fishes. A great variety of fish flourished. Some were armored, others possessed jaws, and some began to breathe air. The most significant breakthrough, however, was the emergence of the first amphibians, vertebrates that left the water to explore the land, signaling the beginning of terrestrial conquest. At the same time, the first extensive forests appeared, composed of tall, tree-like plants that transformed the landscape, stabilized soils, produced oxygen, and laid the groundwork for future terrestrial ecosystems. Continual continental drift continued to reshape shorelines, climate, and habitats.
The subsequent Carboniferous period extended from about 359 to 299 million years ago. The planet became cloaked in lush vegetation. Vast, swampy forests spread across much of the northern continents, especially over the landmass known as Laurasia. These dense forests left behind massive quantities of dead plant material that, over time, was buried and converted into coal, a resource still utilized today. Amphibians diversified further, and the first reptiles emerged, capable of laying eggs on land and living farther from water, a crucial evolutionary leap. During that time, the two great continents, Laurentia and Baltica, slammed together, creating the northern supercontinent often called Euro-America or Laurasia. The impact altered the climate, producing swampy, oxygen-rich environments where life thrived. Atmospheric oxygen rose to its peak, and because of that, some insects, for example dragonflies, grew to gigantic sizes. Next comes the Permian period, which lasted from 299 to 252 million years ago. It was the final chapter of the Paleozoic, both triumphant and tragic. By then, the massive supercontinent Pangaea had finally assembled, gathering almost all of Earth's land into a single, massive block. Reptiles spread across the endless terrain, adapting to a variety of climates and landscapes. Yet the unification brought problems. The interior of the continent was enormous, so the interior regions became extremely dry. Ocean circulation shifted, mountains rose, and the climate grew harsher and more unstable. These changes set the stage for the greatest extinction event in Earth's history, the Permian-Triassic extinction, also known as the Great Dying, which eliminated about 90% of marine species and 70% of terrestrial vertebrates.
One leading explanation links the disaster to massive volcanic eruptions in Siberia that formed the Siberian Traps and released huge amounts of greenhouse gases. The resulting global warming poisoned the oceans and wrecked ecosystems worldwide. Some scientists also argue that the formation of Pangaea disrupted internal planetary processes, worsening the catastrophe. Throughout the Paleozoic, Earth's environment was in constant flux, both literally and figuratively. Warm intervals gave way to glacial periods, especially during the Ordovician and Carboniferous, when glaciers expanded and sea levels fell. As plants spread, particularly in the Carboniferous, atmospheric oxygen increased steadily. This not only supported new life forms, but also allowed some creatures to attain great size. In the oceans, slow plate movements altered water flow, reshaped continents, redistributed nutrients, and created conditions for diverse organisms to flourish. The Paleozoic was not merely a prelude to the age of dinosaurs or a distant lead-in to modern life. It was an era of profound change. Over hundreds of millions of years, life moved boldly from tiny sea organisms to land animals and towering forests. Earth's crust shifted like pieces of a mosaic under the influence of slow but powerful mantle currents. Gondwana and Laurasia drifted toward each other in a gradual collision that ultimately produced Pangaea, reshaping the planet's face. Imagine the Earth's surface not as a solid, unchanging shell, but as a living mosaic, each fragment moving continuously, slowly, silently, yet inexorably. That is the concept of plate tectonics, a revolutionary idea that transformed our understanding of the planet. The outermost layer, the lithosphere, is split into several huge tectonic plates that glide over the softer, more fluid mantle beneath. Though they travel only a few centimeters each year, this patient drift creates the most powerful and impressive features of Earth. Plate boundaries can move apart, slide past one another, or, most dramatically, crash together. The most striking events happen when two massive continental plates converge.
These are not simple pushes. They involve collisions that reshape the planet over tens of millions of years. Such geological giants forge the highest mountain ranges on Earth and leave deep scars that record the history of ancient supercontinents like Pangaea.
A continental collision does not feel like a gentle touch. It is more like trying to sink two large corks into a bucket of water. Both corks stay on the surface, resisting immersion. When oceanic crust meets another plate, its denser, thinner material usually slides down into the mantle. In contrast, the thick, buoyant continental crust simply refuses to sink. Consequently, the meeting edges of colliding continents do not drown. Instead, they crumple, bend, and break, piling up into towering mountains. Imagine a carpet being pushed together from opposite sides. The fabric folds and gathers. Geologists refer to this mountain-building process as orogeny. Mountains are more than jagged surfaces. Beneath them lies a deep, thickened root that extends far into the Earth's interior, much like the hidden keel of a ship. This deep root supports the massive peaks and participates in isostasy, the slow adjustment that raises or lowers mountains as they are worn down by erosion, melting glaciers, and the redistribution of weight. One of the most renowned mountain belts, the Appalachians in the eastern part of present-day North America, originated during the formation of Pangaea. Today, their smooth, rounded slopes look modest compared with the sharp, soaring peaks of the Himalayas. Yet, that impression can be misleading. In ancient times, these gentle hills were part of a colossal mountain system that could rival the Himalayas in height. Their formation did not occur in a single instant. It resulted from a series of large-scale continental collisions that spanned hundreds of millions of years. The most significant episode took place during the Alleghenian orogeny, roughly between 320 million and 280 million years ago. It began when Laurentia, the ancient core of North America, collided with Gondwana, the massive southern supercontinent that included what is now Africa. Earlier geological events had already shaped the region. Prior orogenic phases, such as the Tectonic and Akkadian events, were linked to the closure of the ancient Iapetus Ocean and the impact of volcanic islands and microcontinents on Laurentia. Those early clashes laid the groundwork, but the Alleghenian collision delivered the final, decisive thrust. During this immense collision, pre-existing rock layers were crushed, fractured, and pushed westward. Gigantic slabs of rock, tens of kilometers thick, moved horizontally hundreds of kilometers, creating what geologists call a fold thrust belt. This process gave rise to the Appalachian Mountains. The Alleghenian front marks the outer edge of this grand deformation, a boundary beyond which the Earth's crust was fundamentally rebuilt. The scale of the Alleghenian orogeny is almost unimaginable. Specialists estimate that the ancient peaks could have risen to about 7.5 or even 9 kilometers, comparable with today's Himalayas. This mountain chain stretches for several thousand kilometers and formed the central backbone of the newly assembled supercontinent Pangaea. Over hundreds of millions of years, wind, water, and ice wore down the tallest summits, yet the stone framework of the range has survived. Parallel ridges and deep valleys in the central and southern parts preserve the remnants of massive folds and thrusts, while deep within the mountains, metamorphic rocks such as slate, phyllite, and gneiss bear witness to the intense heat and pressure that accompanied the uplift. To the west, in the adjoining basins, thick deposits of eroded material, sandstone, shale, and conglomerate make up the so-called foreland basins.
These powerful sedimentary layers have swept away what once were majestic peaks. If we now turn our gaze across the Atlantic Ocean toward Russia, we encounter another range with a comparable history, the Ural Mountains. These rugged peaks extend for more than 2,400 kilometers, reaching from the Arctic Ocean in the north down to the Ural River in the south. Like the first range, the Urals arose during the great continental collisions that reshaped Pangaea between roughly 320 and 250 million years ago. Their formation is linked to the Baltic collision, when the European continent met the Siberian landmass and a smaller Kazakhstani bloc. At that time, a narrow Ural Ocean separated these territories. As its floor gradually sank and was consumed by subduction, the continents finally slammed together, giving birth to the mountain chain. Both ranges consist of curved and broken layers of sedimentary, igneous, and metamorphic rocks, and their elongated, narrow shape reflects the narrow zone of ancient impact. However, the Urals have followed a slightly different path. While the first range experienced a humid climate, the Urals have endured long periods of drier, continental conditions.
This has allowed some European-type features to persist better, although over time, erosion has also worn them away. Together, these ancient ranges stand as monumental records of the slow, colossal forces of tectonics, a silent chronicle of an era when whole continents drifted, collided, and rose toward the sky. The Urals stretch from the icy Arctic Ocean across the steppes of Kazakhstan, marking not only the geographic divide between Europe and Asia, but also a profound geological story. Careful study of the rocks shows that the Urals were born from the massive collision of enormous earth fragments, much like two gigantic ships crashing and crumpling together. One of the most compelling pieces of evidence is the presence of ophiolites within the ridge, fragments of ancient oceanic crust that were thrust up and onto the continent. How could such ocean floor be found atop mountains? Only a tremendous tectonic collision, when the ancient ocean was compressed, its bottom folded, and then pushed onto the land, could produce this result. This confirms that, millions of years ago, the area now occupied by the modern Urals was once a vast ocean. Beyond their geological significance, the Urals are unusually rich in natural treasures. Hidden deep beneath the peaks are sparkling veins of gold, placer deposits of platinum, mineral resources, and even beautiful gemstones. These riches did not appear by chance. They are the product of the same powerful forces that built the mountains. These rocks were formed by intense geological activity that accompanied the rise of mountains. When tectonic plates slammed together, enormous heat and pressure were generated. Hot, mineral-laden hydrothermal fluids seeped through cracks, carried metals, and deposited them as dense clusters. Such conditions made the area ideal for creating valuable ore deposits, which is why the Urals have long been regarded as one of the richest mineral belts on the planet. Viewed more broadly, the Urals look like a scar on Earth's surface, tracing the line where two once separate parts of the planet were stitched together. The range marks the collision zone between ancient Asia and ancient Europe, defining the eastern edge of a huge landmass. Later, that landmass, Laurasia, became the core of Pangaea, the supercontinent that joined almost all of Earth's land into a single giant block. The Urals are just one chapter in that massive story. As Pangaea assembled, other mountain ranges sprang up around the world, each born from powerful collisions. For instance, the Appalachian system in North America.
Over time, erosion has softened them, but during the age of tectonic upheaval, they rose high above the surrounding terrain. Another major mountain-building episode, known as the Hercynian or Variscan orogeny, affected what is now Europe. It produced a rugged, winding chain that stretched from Spain and France through Germany to the present-day Czech Republic. This extensive belt formed when small blocks of crust and microcontinents slammed into the southern margin of Laurussia and the larger Gondwana. If we could turn back the clock and reassemble the ancient puzzle of Pangaea, we would see that today's separate ranges, the Appalachians, the Hercynian Belt, and even the Anti-Atlas in North Africa, once formed a single, immense mountain system. That colossal chain, often called the Central Pangaean Mountain Belt, ran through the heart of the supercontinent like a stone spine, and stood as one of the most striking features of the planet at that time. Its tallest peaks, high plateaus, and long ridges stretched for thousands of kilometers, steering wind patterns, blocking rain, and shaping climate, with traces of those effects still visible today. The emergence of Pangaea did not happen without consequences. It reshaped the entire environment. First, the climate changed dramatically. The massive continent covered most of the planet's surface, leaving many interior regions far from the sea to become dry and harsh. In the interior of Pangaea, summers were likely scorching, while winters could be bitterly cold. With no nearby oceans to moderate temperatures, seasonal swings reached extreme levels. Arid conditions fostered the spread of deserts and salt flats, where thick layers of evaporite minerals accumulated over time. At the equator, the picture was entirely different. Dense vegetation thrived in low-lying, humid wetlands, with tall forests and ferns dominating the landscape. Plant material that died over millions of years accumulated, was buried, and eventually transformed into thick coal seams, resources still mined today. Those coal deposits are a direct legacy of the lush, equatorial climate of the Pangaean era. Pangaea also altered the oceans.
As the ancient seas became isolated by the assembling continents, the land was surrounded by a single vast ocean called Panthalassa, which changed the way water circulated around the globe. Ocean currents shifted their direction, and with that change, heat, air, and nutrients were spread across the seas in new ways. Marine life had to adjust. Some species sprang up, while others disappeared. The rise of a supercontinent was accompanied by the birth of gigantic mountain ranges. Over millions of years, those peaks were worn down, and rivers carried sediments and dissolved minerals into the oceans, altering the chemical makeup of the water and possibly steering the evolution of marine organisms. The tale of Pangaea shows the astonishing power of tectonic plates that are hundreds of kilometers thick. They collided slowly, not over centuries, but over hundreds of millions of years, building mighty ranges such as the Urals and the Appalachians. Those mountains are more than beautiful scenery. They are scars from ancient battles of the Earth, proof that the planet is always moving and changing. By studying how these mountains formed, we gain insight not only into the surface of Earth, but also into the deep processes that shape planets. They demonstrate how slow, invisible plate movements create continents, shift oceans, raise mountains, and even influence the course of life itself. Pangaea was more than just a supercontinent. It marked a turning point in history. Its existence affected everything, from climate to the evolution and extinction of species. Yet the Earth never stood still. It is a living, breathing world whose story is carved into stone. The narrative can be read in the folds of mountain ranges, and the future continues to be written by the steady, unstoppable motion of the crust beneath our feet. The idea that all modern continents once formed a single massive landmass called Pangaea is one of the most captivating chapters of Earth's past. Imagine North America, Africa, Asia, Europe, and the rest of the lands welded together into one colossal supercontinent. It sounds like science fiction, but it rests on solid scientific evidence that still amazes people today. For scientists to accept such a bold concept, imagination alone was not enough. Proof was required. Geologists needed reliable, verifiable answers to the key questions. When exactly were the continents joined? And what evidence shows that Pangaea truly existed?
Those answers did not appear instantly. They were gathered painstakingly over many decades. Like detectives solving an ancient mystery, researchers examined rocks, fossils, and deep earth processes. Piece by piece, evidence accumulated. Today, most experts agree that Pangaea assembled about 335 million years ago during the Carboniferous period. The unification did not happen in an instant. For millions of years, the land masses drifted, collided, and merged during powerful geological events. This massive assembly reshaped everything, from climate to the plants and animals that inhabited the planet. To pinpoint when and how it occurred, scientists acted as forensic investigators, studying layers of rock, ancient fossils, and hidden patterns in Earth's magnetic field. One of the strongest clues came from paleomagnetism, the record of ancient magnetism locked within rocks. She works like this. When certain rocks solidify from lava or settle out of water, the tiny magnetic minerals inside them line up with Earth's magnetic field, just like miniature compass needles frozen in time. By comparing rocks of different ages from various continents, scientists could track how those continents had moved. When they arranged the continents to outline the ancient supercontinent Pangaea, the magnetic data from the rocks fit together perfectly. The apparent path of the magnetic pole started the same way on each continent. That provided strong proof that the continents were once joined and shared a common magnetic history. And even more clues lay beneath the oceans. On the ocean floor, researchers found long ridges where new crust is constantly forming. As molten rock rises and cools, it records Earth's magnetic field in the same way as land rocks do. The magnetic patterns on these ridges show that for millions of years, the ocean floor has been spreading, pushing the continents apart. The conclusion is clear. If the continents are drifting away today, they must have been much closer together or even connected long ago. Magnetic evidence wasn't the only clue. Physical features on land also line up. Mountain ranges, rock layers, and overall relief match across opposite sides of the Atlantic. A classic example is the Appalachian Mountains in eastern North America. When the continents are folded back into Pangaea, these mountains line up with the Hercynian Mountains of Central and Southern Europe and with the Anti-Atlas in Northwest Africa.
All three were once part of a continuous central Pangaean mountain belt. Not only do their outlines correspond, but the rock types, stratigraphy, internal folds and breaks are almost identical, like pieces of a puzzle that were cut apart and then reassembled. Another compelling line of evidence comes from ancient continental cores called cratons. By comparing them, scientists showed that the Canadian Shield of North America fits precisely with the Baltic Shield of Europe and the West African craton. These ancient, stable blocks of crust line up like pieces of a global mosaic. Glacial deposits provide further proof. Far apart modern continents, southern South America, South Africa, India, Australia, and Antarctica, contain remnants of ancient glaciers, tillite layers made of glacial debris, striated rocks from ice movement, and U-shaped valleys. At first, this seemed puzzling, because today those regions sit in warm tropical zones where glaciers cannot exist. But when the continents are reassembled into the southern supercontinent Gondwana, all those sites cluster around the South Pole, where massive ice sheets are expected. This early evidence was a key pillar of the continental drift theory. The rocks also reveal ancient climates. During the Carboniferous period, when Pangaea straddled the equator, vast swampy forests covered much of the land. Their remains turned into thick coal seams that we still mine today. Such coal deposits are found in North America, Europe, and parts of Asia, further confirming the once connected nature of these lands. If we were to piece the continents back together as the ancient supercontinent Pangaea, the coal-rich swamps would end up near the equator, where a warm and humid climate would have encouraged the growth of lush vegetation. In contrast, the deserts and arid zones would have been left with deposits of evaporites and minerals such as salt and gypsum, as well as red, iron-rich strata that are typical of dry environments. These dry climate rocks are found in the interior of what used to be Pangaea, exactly where one would expect a large, ocean-far inland landmass to be dry. Their position makes sense only if the continents were once joined. Fossil evidence also tells a clear story. The plant Glossopteris, which looked like a fern with broad, tongue-shaped leaves, produced seeds that were too heavy to be carried long distances by wind or water. Yet fossils of Glossopteris appear on the southern continents of South America, Africa, India, Australia, and Antarctica. The only plausible explanation is that those land masses were once connected, allowing the plant to spread naturally. Its seeds could not have crossed the oceans on their own. All of the magnetic, geological, climatic, and paleontological data combine into a single convincing picture. Roughly 335 million years ago, during the Carboniferous period when coal-bearing forests covered much of the Earth, the separate continents slowly drifted together and formed the massive supercontinent Pangaea. This was not merely a footnote in geological history. It was a pivotal moment that shaped today's mountain ranges and gave rise to the ancient worlds of plants and animals that once roamed a single, continuous land surface. One of the most striking pieces of paleontological evidence comes from a small freshwater reptile called Mesosaurus. About 1 meter long, about the size of a small dog, Mesosaurus lived exclusively in rivers and lakes. Its bones were delicate, and salty seawater was lethal to it, so it could not have survived a voyage across any ocean. Fossils of this creature have been discovered only in 2 distant places, the southern part of Africa and the eastern side of South America. Today, those regions are separated by thousands of kilometers of ocean, but in the distant past, they must have been neighboring shores. Such a limited geographic range is a strong clue that the continents were once joined as part of a larger landmass. Another compelling clue comes from the terrestrial reptile Lystrosaurus. This herbivore, about the size of a modern pig, lived during the late Permian and early Triassic, roughly from 252 to 248 million years ago. Unlike Mesosaurus, Lystrosaurus walked on dry land and could not have crossed any ocean. Yet its fossils have been found on 3 widely separated continents: Antarctica, India, and South Africa. The fact that the same land animal appears on all 3 continents tells us that those lands were once connected, forming the southern portion of Pangaea known as Gondwana. The age of the Lystrosaurus fossils lines up exactly with the time when geologists believe Pangaea had fully assembled, reinforcing the case. A further example is the land-dwelling reptile Cynaegnathus, which was roughly the size of a dog. Its fossils, like those of Mesosaurus and Lystrosaurus, are scattered across continents that are now far apart, adding yet more support to the idea that all these pieces once fit together to form the great ancient supercontinent. Lystrosaurus could not swim across an ocean, yet its fossils have turned up in South America and Africa. That pattern suggests the continents once formed a single landmass. The evidence goes beyond just these bones. Scientists today are uncovering matching fossils of ancient amphibians, reptiles, early mammals, and plants on continents that are now far apart. Most of those creatures lived only on land or in fresh water, so they could not have crossed the vast seas that separate the continents now. The correspondence of the fossils tells a clear, consistent story. Long ago, the continents were joined together in one huge supercontinent. The strength of this story comes from how well the different kinds of evidence fit together. It isn't only about fossils. Researchers have examined the direction of ancient magnetic fields locked in rocks, paleomagnetism, compared rock layers and mountain chains across continents, and studied old climate patterns. All of these lines of inquiry point to the same conclusion: Pangaea really existed. Pangaea formed about 335 million years ago, during a period of dramatic changes on Earth's surface. The coming together of the continents created massive mountain ranges, altered the flow of air and water around the planet, and had a huge impact on the evolution of life. With a single, sprawling land area, plants and animals could move freely, and new species appeared in response to the altered conditions. The fossil record gives us a window into that ancient world, letting us picture a time when Lystrosaurus and Mesosaurus roamed a continent that is now split by oceans. This isn't just dry scientific fact. It is a vivid reminder that the planet is always in motion. The land beneath our feet participates in a slow but relentless dance. Over millions of years, the continents drift, collide, and reshape the planet. The formation of Pangaea marked a turning point in Earth's history, setting the stage for everything that followed: the shape of the world and the development of life itself. Imagine a world where traveling from one edge of the land to the other meant crossing not just a few countries or mountain ranges, but a piece of land the size of an entire planet. In such a world, the idea of a sea voyage from one continent to another would have been meaningless, because there was only one colossal landmass covering almost the whole globe. That was Pangaea, the last great supercontinent of ancient Earth, a single continent that persisted for tens of millions of years. At the heart of this massive continent lay a vast interior far removed from any ocean. The interior deserts of Pangaea were enormous, dry, and ruthless places where the climate was not merely harsh, but truly brutal. Without the moderating influence of ocean breezes and humid sea air, the interior became a realm of scorching heat, biting cold, and relentless drought. Think of how immense this land was. No modern continent can compare to the sheer scale of Pangaea. It stretched from the frozen realms of the northern poles all the way to the icy territories of the south, covering almost the entire continental crust. Today, even the massive continents such as Asia and Africa are bordered by oceans, which moderate temperature and deliver moisture. In the time of Pangaea, the situation was completely different. The supercontinent's sheer size amplified its continental character, pushing the climate far from any oceanic influence, a condition that is virtually unattainable now. Moist air over the ancient Tethys Sea or the extensive Panthalassa would have had to travel across thousands of kilometers of land before reaching the interior of Pangaea. During that journey, it would have shed nearly all of its humidity. By the time any remaining moisture arrived at the center, the air would have already been dry and laden with dust. Compounding the problem were the towering mountain ranges that rose when separate land masses collided. These ranges formed gradually as Earth's tectonic plates converged. Picture the modern Appalachians, the Scottish Highlands, and the ancient Hercynian or Variscan Mountains, once soaring across Europe and northern territories. Many of these peaks could have matched the heights of today's Himalayas, or even exceeded them. Not only were they lofty, but they also extended for thousands of kilometers, acting like colossal stone barriers that blocked rain clouds from moving deeper inland. What unfolded was this. Humid oceanic breezes moving toward the continent's interior were forced upward by the mountain walls. As the air rose, it cooled, releasing its moisture as rain or snow on the windward slopes.
Small verdant pockets resembling oases could appear there, but on the leeward side, the air descended dry and hot, creating vast rain shadow zones where precipitation was virtually absent. These rain shadows didn't merely dry the ground, they gave rise to immense, water-free deserts that could stretch for thousands of kilometers. There were no modern equivalents for the heart of Pangaea. Imagine endless seas of red-gold sand continually reshaped by fierce, ever-shifting winds. Some sections might have resembled the Sahara or the Arabian Desert, yet they would have dwarfed them many times over. The relentless wind buried ancient landscapes under dunes, only to uncover them again centuries later. Other portions of the interior consisted of broad, rocky plains or high, flat plateaus where virtually nothing could grow. Occasional rains might have filled shallow lakes or inland seas, but the sun rapidly evaporated the water, leaving behind glittering salt flats that stretched to the horizon. The ground often took on reddish-orange hues as iron-rich rocks oxidized, leaving the kind of strata that geologists today interpret as evidence of long-lost deserts. The climate at Pangaea's core was as extreme as its terrain. Massive land masses stored daytime heat, and with no nearby oceans to moderate it, temperatures swung wildly. Daytime could become scorching, lethal to most life forms, while evenings brought a swift plunge into freezing cold. The contrast between day and night was stark, and seasonal changes only amplified these extremes. Summers burned with intense heat, whereas winters were bitterly cold and harsh. The air over the supercontinent was often bone dry, thick with dust lifted by relentless winds. Yet Pangaea's influence was not confined to its central region. It reshaped the weather of the whole planet. This single, enormous landmass surrounded by the world's oceans altered the movement of air and water on a global scale. During the hot summer months, the land heated up far more quickly than the adjacent seas, creating a massive, low-pressure zone near the surface that drew in moist oceanic air. That influx gave rise to gigantic monsoons, seasonal wind systems far more powerful than any modern counterparts. Coastal areas could experience heavy rains during these months, but rain seldom reached far inland. As the air moved toward the interior, the clouds had already relinquished most of their moisture, leaving the interior deserts as dry as ever.
In winter, the opposite pattern occurred. The arid interior cooled rapidly, generating high-pressure zones that pushed cold, dry air outward, further desiccating the continent. The constant shifting of these massive air flows, produced by Pangaea's sheer size and unusual shape, created chaotic and forceful worldwide weather patterns. It is impossible to overstate how strange and severe Earth's climate was in that era. The interior of Pangaea was not merely dry, It was a realm of extremes, scorching heat and bitter cold, endless deserts and towering mountains, relentless dust storms, and forgotten inland seas. Fossils and the surviving lineages of ancient organisms tell us that this supercontinent dramatically molded Earth's climate and left a profound imprint on the planet's history. Pangaea's surface was not only a chain of lofty, majestic ranges. It consisted of a varied mosaic of open plains, high plateaus, deep valleys, and shifting depressions. A great mountain belt, the Appalachian Range, spanned the northern and central parts of the supercontinent, shaping the terrain and giving rise to many striking features. Between the high, broad plateaus lay ridges and low-lying basins. Some of these basins were dry and dusty, while others held shallow seas or temporary lakes, especially during the warm periods when the water cycle intensified. Depending on altitude and proximity to these vast water bodies, moisture sources could change seasonally or over millions of years. In wetter intervals, the basins sometimes filled with water, becoming inland seas or expansive salt lakes. More often, however, the sun-baked lands remained arid, with strong winds sweeping sand into thick deposits. Over time, evaporating water left behind salt crusts and evaporite layers, evidence of ancient dryness. The Permian period, lasting up to 252 million years ago, marked the beginning of the first stresses that would eventually lead to Pangaea's breakup. In some regions, the continental crust stretched and thinned, revealing the earliest cracks that formed incipient rift valleys, then large, low depressions that occasionally collected water, giving rise to narrow lakes or seasonal streams. Where these rifts deepened enough, magma rising toward the surface could trigger volcanic activity, especially within the interior of the landmass. Nonetheless, the largest volcanoes mostly clustered along the margins of Pangaea, mere zones where oceanic crust was being forced beneath the continental shelf in a subduction process. The river systems of Pangaea were truly remarkable. The continent stretched nearly from pole to pole, so moving water across its surface required enormous rivers. Yet many of these rivers never reached the ocean, disappearing into interior basins or evaporating before completing their journey. Rivers poured into the arid interior of the supercontinent and finally disappeared into inland basins, where the water evaporated and left behind flat, dry lake beds, salty pans, or sparkling salt marshes. Only a few rivers managed to reach the great ocean that surrounded the land. The Pangaea was truly immense. It drained huge portions of the continent and stretched across vast distances. Unlike today, when many smaller continents are bordered by oceans, Pangaea offered only a few routes for rainwater to flow to the sea, so its whole water cycle was different. Yet the weathering and erosion that occurred across the dry interior still affected the chemical makeup of the oceans. If we look at the climate of Pangaea during the Permian period, we see a world that was both strange and harsh. Carbon dioxide levels in the atmosphere were far higher than they are now, keeping the planet generally warm, but the heat was not spread evenly. Because the landmass was so huge, it warmed up and cooled down very slowly, a property scientists call thermal inertia or climatic inflexibility. Consequently, the temperature gap between the scorching equator and the freezing poles was large, and the seasons were very pronounced. The poles, being part of the same continuous land, probably endured long, frosty winters and seasonal floods that could produce extensive ice sheets. Compared with the earlier Carboniferous, when the Earth was covered by widespread glaciation, the Permian world was mostly free of ice.
Evidence for this ancient climate comes from the rocks and fossils scattered across the continents today. Coal seams, which form in warm, swampy environments, appear only in narrow strips along the receding margins of Pangaea, indicating that most of the interior was too dry for thick forests and marsh vegetation. In contrast, the central and subtropical regions are rich in red beds and extensive salt deposits. The climate of Pangaea was marked by sharp contrasts.
Without the moderating influence of surrounding oceans, huge deserts emerged, powerful wind systems developed, and rain shadows formed behind massive mountain ranges. The sheer size of the land shaped winds and weather patterns for the entire planet. Life had to cope with searing summers, bitter winters, dry winds, and the lack of water. Plants and animals needed endurance, ingenuity, and special adaptations to survive such harsh conditions. Today, as we study the fragmented rocks of Pangaea across the continents like pieces of a mosaic, we see traces of that ancient world. These clues tell us not only about the surface of the Earth, but also about how climate and land together determined the fate of life. The history of Pangaea is more than a story of old stones and barren deserts. It powerfully reminds us that the shape and size of a continent can set the rhythm for the whole planet. The Permian period became one of the most dramatic and transformative chapters in Earth's long history. It lasted from 399 to 252 million years ago, when the supercontinent finally assembled into a single massive landmass and reshaped the face of the Earth. As the continents closed like giant pieces of a puzzle, everything began to change. The outlines of oceans, the movements of air and water, and most importantly, the life that walked, crawled, floated, and grew on the land. The Permian era was a time of both great achievement and deep loss. Life on the planet grew more varied and better suited to shifting environments, yet the period concluded with the most catastrophic mass extinction in Earth's history, wiping out the majority of species and paving the way for the age of dinosaurs. To grasp what the Permian was like, one must become familiar with the animals and plants that inhabited it, and see how the massive supercontinent Pangaea influenced their ecosystems. At the start of the Permian, terrestrial life was still feeling the after effects of the Carboniferous, though the extreme swamps and gigantic insects of that earlier age were fading. The ancient coal-bearing wetlands had been lush, damp, and full of early amphibians. As Pangaea continued to assemble, the global climate grew drier, harsher, and more strongly seasonal. Rainforests receded, deserts spread, and organisms had to adapt quickly or disappear. In the early part of the period, especially along rivers and wet coastal zones, remnants of the old swampy vegetation persisted. Primitive trees such as club mosses, seed ferns, and sphenopsids shared the landscape with towering horsetail-like plants and numerous ferns. These water-loving plants thrived in moist soils and built thick peat layers that, over millions of years, transformed into the coal we mine today. Yet the climate was changing. Rain fell less regularly, temperatures swung more sharply, and moisture-dependent plants began to retreat. Gymnosperms stepped into the vacant niches, thriving on the increasingly arid lands of Pangaea. Conifers, cycads, and other seed-bearing plants gained an evolutionary edge because they reproduced by seeds rather than by water-dependent spores. The sturdy seed coats protected embryos through dry spells, allowing them to sprout when rains returned. Wind-carried pollen freed them from the need for standing water, while waxy, tough leaves limited water loss, making them well-suited to deserts and dry forests. Among the most notable and abundant Permian plants was Glossopteris, a seed fern that blended fern-like fronds with seed-bearing reproduction. Glossopteris bore broad, tongue-shaped leaves and formed dense forests across the southern portion of Pangaea, covering what are now South America, Africa, India, Antarctica, and Australia. Fossils of Glossopteris on all these continents later served as key evidence for Alfred Wegener when he proposed continental drift, helping scientists confirm the existence of Pangaea. These forests played a crucial role in Permian ecosystems, offering shelter, food, and nesting sites for many animals, especially herbivores that fed on leaves and seeds. The animal life of the Permian was equally remarkable. The land was dominated by synapsids, a group that was not quite reptilian in the modern sense, but would eventually give rise to mammals, earning them the nickname mammal-like reptiles. In the early Permian, pelycosaurs were especially widespread, with the most famous example being Dimetrodon, known for its large sail on the back. The sail may have helped regulate body temperature, warming the animal in the morning sun or cooling it during the heat of the day. Pelycosaurs appeared in many shapes and sizes, ranging from large predators to small insect hunters. Over many millions of years, the primitive pelycosaurs were gradually replaced by a more advanced lineage of synapsids known as therapsids. These animals possessed much stronger jaws, razor-sharp teeth, and a highly efficient way of moving across the land. In several respects, their bodies and habits already hinted at the traits we see in modern mammals. Among the therapsids, the dinocephalians stood out as the largest creatures of their era. This group included bulky herbivores with massively thick skulls, such as Esteminosuchus, which bore odd horn-like protrusions on its head, as well as fierce predators like Ankylosaurus, perfectly built for hunting. Fossils of both types have turned up in South Africa and Russia, showing that they occupied a broad swath of the supercontinent. Another prominent branch were the Dicynodonts, a peculiar group of herbivores equipped with a beak and a pair of tusks. Their size ranged from small, dog-sized burrowers to giants as large as a hippopotamus. The name Dicynodont literally means two dog teeth. One of the most successful members of this lineage was Lystrosaurus. Remains of this animal have been discovered on every continent, even in Antarctica, which testifies to the close connections between the land masses at that time. Its ability to dig likely helped it endure droughts and evade predators. The most fearsome hunters of the Permian were the Gorgonopsians, saber-toothed predators with long canines and powerful jaws that could rip their prey apart. Species such as Gorgonops and Innostrancevia sat at the top of the food chain, often preying on numerous Dicynodonts. Thus, the principal actors of the Permian were the synapsids alongside the early reptiles that were beginning to appear. On the ground, heavily armored giants like Scutosaurus wandered, resembling a cross between a turtle and an armadillo. Smaller, fleet-footed forms such as the Procolophonians also existed. In the late Permian, archosauromorphs, the ancestors of dinosaurs and crocodiles, emerged, although the dominant therapsids remained relatively modest in size and largely unnoticed. Amphibians persisted mainly in moist habitats. Giant temnospondyls, akin to enormous frogs, inhabited rivers. The skies buzzed with insects, from cockroaches to dragonflies and the earliest beetles. The sheer size and uninterrupted expanse of Pangaea had a profound impact on all living things. Climate extremes developed. The interior of the supercontinent became scorching and arid, while the coastal zones stayed comparatively wet. This created intense environmental pressure that forced both plants and animals to adapt to harsh conditions. With no oceans or mountain ranges to block movement, species could spread across vast distances. Consequently, organisms such as Lithospheric and the plant Glossopteris came to dominate huge territories, leaving clues that modern scientists use to reconstruct ancient continental connections. Around 252 million years ago, at the close of the Permian, a massive catastrophe unfolded. Whether driven by colossal volcanic eruptions, a sudden climate collapse, or a combination of factors, about 90% of marine life and 70% of terrestrial life vanished. This event stands as the greatest mass extinction in Earth's history. Though it brought widespread death, it also cleared ecological space, allowing new groups to rise. In the quiet that followed, life began to reorganize, setting the stage for the next great chapter, the age of the dinosaurs. When the continents came together to form the mighty supercontinent Pangaea, a cascade of changes swept across the planet, reshaping ecosystems, animal habits, plant distributions, and the very paths of evolution. This massive landmass existed from roughly 299 million years ago until about 252 million years ago, and its influence extended far beyond simple geography. Because almost all of Earth's terra firma merged into a single expanse, the barriers that once kept terrestrial organisms apart vanished. Animals that had been confined to isolated land masses could now traverse the great interior, and wind and water could carry plant seeds across distances that previously seemed insurmountable. Regions that once nurtured unique, endemic species began to lose that isolation, a phenomenon scientists refer to as a decline in provincialism. On separated continents, species evolved independently. On Pangaea, many areas hosted very similar or even identical organisms. A striking illustration of this mixing comes from the fossil record. Remains of the seed fern Glossopteris and the herbivorous therapsid Lithospheric have been uncovered on continents that today lie thousands of kilometers apart: South America, Africa, Antarctica, and India. Their widespread presence testifies to how freely life could spread across the unified land. The supercontinent spanned a tremendous range of latitudes, giving rise to an extreme variety of climates. The interior, far from any ocean, was arid, hot, and barren, while coastal zones experienced milder conditions and seasonal monsoons that delivered heavy rains. Plants and animals had to adapt to these divergent environments. Drought-tolerant gymnosperms with tough leaves and protected seeds flourished inland, whereas the lush, moisture-loving swamp forests that once covered much of the planet persisted only in humid coastal strips and deep rift valleys where water remained plentiful. Among the animals, many Permian synapsids, the ancestors of mammals, developed clever strategies to cope with dryness. Some dug burrows to escape the heat, others altered their diets toward tougher but more abundant food sources. Because the same climatic zones stretched over vast areas, these adaptations proved useful across much of Pangaea. With a continuous landmass, migration became far easier. Species were no longer stranded on isolated continents. If their local environment grew too dry, cold, or crowded, they could simply move toward more favorable habitats. Some likely trekked thousands of kilometers in search of food, shelter, or mates, tracking shifting climates as they changed. However, this freedom also intensified competition. Predators could pursue prey across great distances, forcing prey to keep moving to avoid becoming targets. The global connectivity of ecosystems made survival more challenging. Finally, the unification of the continents probably curbed the emergence of new species. By reducing geographic isolation, Pangaea limited the opportunities for populations to diverge and evolve independently,
leading to a slowdown in speciation rates during its reign. One of the principal ways new species appear is when groups become isolated by oceans, mountains, or other big barriers, allowing them to change independently over time. Experiment sponsors call this process allopatric speciation. On the supercontinent Pangaea, however, natural barriers were scarce. Rivers and smaller mountain ranges existed, but they rarely kept populations apart for long periods. As a result, many species stayed in contact across great distances and rarely had the chance to evolve on their own. This likely explains why global biodiversity during that time was lower than it became after the continents split, and why the total number of species was smaller. In other words, many organisms were widespread, but the overall variety of life was poorer.
Earth's ecosystems were tightly linked, which also made them more uniform. The enormous expanse of land allowed terrestrial ecosystems to grow dramatically in size and complexity. During the Permian period, a new continent emerged on the surface, giving rise to many novel forms of life. One of the dominant animal groups were the theropods, early beast-like reptiles that would later give rise to mammals, and they thrived in the dry, seasonal landscapes of Pangaea. At the same time, the plant world was taken over by cone-bearing gymnosperms, such as ancient relatives of pines and cycads. Together, these plants and animals filled the vast open spaces, turning deserts and plains into active ecosystems. Marine life remained rich, but the focus of evolutionary innovation shifted to the continents, where new challenges and opportunities directed the development of organisms. Ironically, the very connectedness that helped species spread also made them vulnerable to planet-wide disasters. Because ecosystems were linked, a single catastrophic event could affect the whole world. That is exactly what happened at the end of the Permian, about 252 million years ago. Massive volcanic eruptions in what is now Siberia created the Siberian traps and released enormous amounts of carbon dioxide into the atmosphere. The planet likely warmed sharply, turning many regions into scorching, dry wastelands. Pangaea was relatively uniform, offering almost no isolated refuges where organisms could escape the harsh new conditions. With nowhere to hide, many species perished, contributing to the Permian-Triassic extinction, the most destructive event in Earth's history. Roughly 90% of marine species and about 70% of terrestrial species vanished. The story of life on Pangaea combines extraordinary unity with extreme fragility. The joining of continents created a world where plants and animals could move freely, where new terrestrial ecosystems arose, and where adaptations to dry, harsh environments became essential for survival. Yet that same unity meant that a single disaster could wipe out life everywhere at once. Pangaea determines how the slow dance of tectonic plates can reshape the planet in both beautiful and terrifying ways. Life on the supercontinent was simultaneously a triumph of evolution and a sacrifice to the ever-changing nature of Earth. Imagine an era when a global catastrophe, like a massive volcanic eruption, swept across the planet, leading to a crisis that eliminated nearly 90 out of every 100 marine species and about 70 out of every 100 land animals. A truly catastrophic episode in Earth's history unfolded roughly 252 million years ago, an event scientists refer to as the Permian-Triassic extinction, often called the Great Dying. It wasn't an exaggeration to call it the most devastating extinction in the past 4.5 billion years of Earth's existence. It was as if the biosphere had to squeeze through a narrow doorway of survival, and most species simply could not pass. The few organisms that did survive required millions of years to rebuild the ecosystems. Before that calamity struck, the planet looked very different from today. All of the continents were fused together into a single supercontinent named Pangaea, which stretched almost from the North Pole to the South Pole. That unusual shape created climate patterns and ocean currents unlike anything we experience now. Deep inland, far from any sea, the land was arid and harsh, with scarce rain and extreme temperature swings. Along the coasts, the climate was milder, sometimes even tropical, with alternating wet and dry seasons, reminiscent of modern monsoons. Even with those challenges, life thrived. The seas teemed with a dazzling array of creatures, numerous invertebrates, brachiopods, trilobite-like arthropods, and vibrant coral reef communities. On land, the dominant animals were the synapsids, ancient relatives of mammals. Among them were the formidable gorgonopsians, predators armed with razor-sharp teeth, and the more peaceful dicynodonts, herbivores bearing beaks and tusks. One of the most common herbivores was Lystrosaurus, a stout, small animal that would later face the impending apocalypse. Forests of conifers, cycads, and ferns draped the continent in green canopies, supporting intricate food webs. The world may not have been as bright or lively as today's Earth, but it pulsed with abundant life. Beneath that seemingly ordinary surface, massive forces were gathering. The most plausible trigger for the global disaster was an enormous series of volcanic eruptions that occurred in what is now Siberia, northern Asia. It wasn't a single volcano, but a vast region known as the Siberian Traps, where lava erupted through huge fissures that persisted for perhaps 1 million years.
Imagine rivers of molten rock spilling from deep, gaping cracks hundreds of meters wide, spreading across the landscape and forming thick basalt layers that in some places reached thousands of meters in depth. Scientists estimate that millions of cubic kilometers of lava poured out, enough to blanket entire continents. The danger, however, extended far beyond the lava itself. The eruptions spewed colossal quantities of gases into the atmosphere, chiefly carbon dioxide and sulfur dioxide. While sulfur dioxide can initially cool the planet by reflecting sunlight, the overwhelming release of carbon dioxide eventually trapped heat, turning the world into a scorching greenhouse. Moreover, the lava penetrated not just solid rock, but also underground deposits of coal, oil, and salt, releasing additional toxic gases. Among these were methane, a greenhouse gas even more potent than carbon dioxide, and compounds containing chlorine and fluorine that could harm living organisms in other ways. Together, these forces triggered an atmospheric disaster of a scale never before seen on Earth. At first, massive sulfur releases could have plunged the planet into a brief volcanic winter, cooling the climate for a short time. In this case, however, that cooling faded quickly. An unrelenting flood of carbon dioxide and methane then drove temperatures upward at a rapid pace. Within a comparatively brief interval in geological terms, by the standards of the era, global temperatures could have risen by more than 10 degrees Celsius. Such a jump was enough to turn once lush forests into deserts and make the tropics almost inhospitable for most life. The warming happened so fast that neither plants nor animals had time to adjust. Forests dried out, rains ceased, and vast stretches of land cracked and withered. As the vegetation weakened and died, the herbivores that depended on it vanished, followed shortly by the carnivores that hunted them.
The entire terrestrial food web began to collapse. The most dramatic changes, however, unfolded in the oceans. As the water warmed, it retained less dissolved oxygen, the same element marine organisms need as much as land animals. The warmer the seas became, the sharper the drop in oxygen, and the larger the expanding dead zones. Simultaneously, the oceans soaked up enormous quantities of atmospheric carbon dioxide, becoming increasingly acidic. Corals, mollusks, and plankton found it almost impossible to build shells or skeletons. With these tiny yet vital members of marine ecosystems failing, the whole oceanic food chain started to crumble from the bottom up. Oxygen depletion and rising acidity caused massive die-offs throughout the seas. Areas that once teemed with vibrant, diverse communities turned hot, sour, and nearly lifeless. The Permian-Triassic, or Great Extinction, left the land scarred and silent. Forests thinned, oceans fell quiet. Life did not disappear entirely, but it was nearly wiped out. Earth's ecosystems required millions of years to recover, eventually emerging with new forms that filled the vacant niches. Yet some species endured the unimaginable catastrophe. A hardy little creature called Lystrosaurus survived and spread across the continents. From the ashes of extinction, evolution eventually gave rise to the age of dinosaurs and, much later, to our own lineage. Imagine the planet's oceans transformed into immense, lifeless pools of poison. During the greatest extinction in Earth's history, the most terrifying shifts occurred beneath the waves. As the ocean warmed, its oxygen content fell dramatically. Surface waters, normally rich in life-sustaining oxygen, stopped mixing with the colder, deeper layers, turning the seas into a layered cake of stratified water. Oxygen remained only at the surface, disappearing below. Without this mixing, the deep ocean became a suffocating void. Yet the deadly changes were not confined to the depths. Anoxic zones, areas completely devoid of oxygen, began to rise, encroaching on shallower waters and turning once thriving habitats into silent graveyards. Fish, corals, mollusks, and countless other creatures that had filled these waters started to die off en masse. The horror did not stop there. In the oxygen-poor waters, unusual green sulfur bacteria that do not require oxygen proliferated. These microbes released hydrogen sulfide, a poisonous gas that smells of rotten eggs. As hydrogen sulfide accumulated, a new nightmare took hold of the oceans. Widespread, toxic, and deadly conditions that reshaped marine life forever. A condition in which water loses its oxygen and becomes saturated with a poisonous gas turned the oceans not merely lifeless, but outright toxic. The evidence of that nightmare is locked in the rocks. Around the globe, scientists discover layers of black shale that are rich in organic material and sulfur, which point to the presence of deadly, poisoned waters. It is as if the Earth itself kept the memory of the time when its seas darkened, filled with a foul stench, and became lethal to almost all life. The consequences were truly catastrophic. Tiny plankton and coral reefs vanished, along with huge fish and even the top marine predators. Some of them were killed by hydrogen sulfide, others simply suffocated. The thermocline, the invisible boundary separating warm surface water from colder deep water, rose, bringing toxic, oxygen-deprived water closer to the surface and turning what once was a safe habitat into a death zone.
Marine ecosystems that had flourished for millions of years were destroyed almost instantly. Then the situation worsened. Scientists believe that the hydrogen sulfide did not stay confined to the oceans. A portion of the gas escaped into the atmosphere, where it could poison land animals and even damage the ozone layer, the shield that protects life from dangerous ultraviolet radiation. When the ozone weakened or disappeared, sunlight became deadly, scorching plants and animals and likely contributing to mass deaths on land. A violent chain reaction followed. The poisoned oceans fouled the sky, and the poisoned sky brought even more death back to the land. But the nightmare was not the result of a single event. It was the outcome of a whole network of mutually reinforcing disasters. At its center lay the Siberian Traps, a vast region in what is now Russia, where about 252 million years ago, gigantic eruptions began. For roughly 1 million years, they poured out lava and gases, injecting colossal volumes of carbon dioxide into the atmosphere. The planet began to heat up, and as temperatures rose, clathrate deposits, ice-like formations of methane deep beneath the ocean floor and in frozen ground, melted. These clathrates had trapped methane, a greenhouse gas far more potent than carbon dioxide. The release of methane accelerated warming even further, as if fuel were being added to an already raging fire. Some scientists argue that large-scale fires, sparked by drought and atmospheric changes, added even more carbon to the air. Oceanic currents shifted, making the distribution of oxygen across the seas more difficult. Each disaster amplified the others: warming oceans, deadly gases, suffocating life, and a poisoned sky. The Earth became caught in a lethal feedback loop. The destruction reached a level the planet had never seen before and has not seen since.
About 90% of all marine species disappeared. On land, roughly 70% of vertebrate species perished. Ancient creatures that had survived for hundreds of millions of years vanished forever. The famous trilobites, which had existed since the Cambrian period, were gone. Blastoids, relatives of marine animals, became extinct, as did many brachiopods, crinoids, and ammonoids, which survived only in a few scattered forms. The giant predators that once roamed the land, including the gorgonopsids, were wiped out. Only a handful of hardy survivors persisted, such as Lystrosaurus, a squat, pig-sized animal that resembled a reptile. Even among the once dominant groups that gave rise to mammals, most were wiped out. The whole living network collapsed. Scientists refer to this as the selectivity of extinction. Some organisms survived the heat, the low oxygen, or the acidified seas, but most could not. The survivors were aided by chance, resilience, or special adaptations. When the worst passed, the planet fell into a deep silence. The early Triassic, often called a dead zone, followed. Only a few hardy species persisted. Most survivors were small, a phenomenon known as the Lilliput effect, because large forms could not endure the harsh conditions. The world was ruled by a handful of disaster-tolerant groups, such as Lystrosaurus, which managed to live where almost everything else perished. Rebuilding life took millions of years, and when it finally did, the world was different. Extinction opened empty ecological niches that new lineages had to fill. Over time, this slow recovery led to the rise of dinosaurs and, much later, mammals. From the devastation of the Great Extinction emerged the foundation of the modern world. Scientists keep investigating this extraordinary episode. Today, using powerful tools, they examine ancient rocks and sediments for chemical clues. They compare volcanic eruptions, climate shifts, and oceanic oxygen levels, and they construct complex models of possible chain reactions. Although experts still debate many details, there is broad agreement that eruptions of the Siberian traps ignited the fuse of a global catastrophe. The Great Dying not only ended an era, it completely rebooted life on Earth. It serves as a stark reminder of how tightly the planet's systems are linked and how rapidly everything can collapse when balance is lost. From poisoned oceans to skies filled with lethal gases, the world 252 million years ago faced a disaster that nearly erased life. Yet after a long, painful interval, life rose again from the darkness, smaller, more modest, and ready to begin a new chapter. Imagine a planet slowly emerging from the ashes of the greatest biological catastrophe in its history. That was Earth at the dawn of the Triassic. The Triassic period, which began about 252 million years ago and ended roughly 201 million years ago, followed the Permian-Triassic extinction event, a mass killing that destroyed almost all marine life and a huge number of terrestrial species. The Triassic started in an almost empty world and concluded with another, less severe extinction that still reshaped life. Between these two extinctions, life returned, slowly, painfully, and in surprising forms. Terrestrial ecosystems began to recover. It was a time of fresh starts, a biological reset. Plants and animals evolved new habits, new forms, and filled the vacant ecological space. In the Triassic, the first dinosaurs and their earliest mammalian ancestors appeared, our distant relatives. Opportunities, the struggle for survival, and relentless competition paved the way for grand evolutionary changes. After the loss of so many species, the survivors found themselves with few competitors and many open niches. Life once again had room to grow and experiment. The world during the early Triassic looked nothing like today. Almost all of the continents were fused into a single massive supercontinent called Pangaea, which stretched from one pole to the other and was surrounded by a huge ocean named Pangaea. Because the interior of Pangaea lay far from the moderating influence of the sea, its central regions were extremely hot and dry under an unrelenting desert sun. The coasts, however, were not uniformly arid. Fossil evidence of plants and rain marks shows that some shoreline zones experienced strong seasonal monsoons and brief but intense storms that dumped large amounts of water in a short time. Across the whole planet, the climate stayed very warm. There were no polar ice caps, and the ocean waters remained relatively warm and sluggish, still recovering from the great extinction that had just occurred. The lack of cold currents meant that the seas held less oxygen, which made it difficult for marine life to bounce back. After the devastating Permian extinction, the land appeared empty and lifeless. In the early spring, only a few tough, fast-growing plants managed to take hold. One such pioneer was a delicate, thin-steamed spore plant called Pleuramia. Over time, life began to return. By the middle and late part of the early Triassic, forests started to spread again. Tall conifers that looked like palms, together with cycads and ginkgos, covered large areas, providing shelter and food for the growing animal populations. These woodlands laid the groundwork for more intricate food webs and more stable ecosystems. Immediately after the Permian extinction, Earth's ecosystems were simple and crude, dominated by a small number of very fortunate survivors. Paleontologists refer to these resilient organisms as disaster taxa, species that managed to persist through the worst mass extinction in Earth's history. One of the best-known examples is Lystrosaurus, an unusual creature about the size of a pig. It had a stout, barrel-shaped body, short tusks, and a snout that resembled a bulldog's. Lystrosaurus belonged to the dicynodonts, a group of herbivorous synapsids that are distant relatives of mammals. This hardy little animal spread extremely widely. Its fossils have been found in Antarctica, South Africa, India, and China, all of which were then part of the southern portion of Pangaea, known as Gondwana. Because it was so successful, Lystrosaurus earned the nickname the Triassic Ark. It was one of the few animals to survive the extinction and then thrive afterward. Scientists think Lystrosaurus survived thanks to its simple diet, ability to tolerate low oxygen conditions, and overall hardiness, which gave it a huge advantage in the harsh early Triassic world. As the planet continued to recover, new groups of animals appeared. Among the most important were the early archosauromorphs, a lineage of reptiles that would later give rise to crocodiles and dinosaurs. These archosauromorphs looked like long-legged lizards. Many were small and quick, but they possessed several evolutionary benefits. Their lungs operated more efficiently, their bodies held a more upright posture, and their movements were powerful, yet required less energy. These traits gave them a clear edge as ecosystems grew more complex. Approximately 230 million years ago, the first true dinosaurs emerged. At first, they were not giants. Early dinosaurs were generally small, bipedal, and built for fast running. Some of the oldest known species, Eoraptor, Herrerasaurus, and Styracosaurus, have been discovered in an Argentine formation called the Ischigualasto, a rich fossil site that preserves a vivid picture of life in that era. These early dinosaurs were agile hunters, poised to begin the long rise that would eventually dominate the Mesozoic world. Even the most massive modern animals could not match it in size. Their teeth were sharp, and people often speak of their carnivorous habits. They either chased down small prey or scavenged on dead flesh. The vertical stance of their limbs let them sprint, and the forelimbs likely were used to seize and hold. Yet early dinosaurs had not yet become the rulers of the land. That position was still held by other archosaur lineages. While dinosaurs were just beginning to gain strength, the world was ruled by the Pseudosuchians, distant relatives of crocodiles. This group comprised many formidable beasts. Phytosaurs looked like crocodiles, but their nostrils sat high on the skull, allowing them to stay mostly submerged. Atosaurs were herbivores armored like tanks. There were also Rauisuchians, fierce terrestrial predators resembling giant, upright crocodiles. They sat at the top of the Triassic food chain, while dinosaurs lingered in the shadows, waiting for their turn. At the same time, another lineage was undergoing a quiet evolutionary revolution. These were the cynodonts, the ancestors of mammals. In the Permian, synapsids ruled, but the Great Extinction wiped out most of them, leaving only a few survivors. The cynodonts began to change gradually but profoundly. They developed specialized teeth, sharp incisors, pointed canines, and grinding molars, making it easier to chew food, which is crucial for animals with high energy demands. A secondary palate formed, separating the nasal passage from the mouth, so they could chew while breathing. The lower jaw transformed. Some of its bones reduced in size and eventually migrated into the middle ear, a key feature of modern mammals. This transition is clearly visible in fossils such as Tritylodon and Cynognathus. Although they still resembled reptiles in many ways, they increasingly looked and behaved like mammals. Some researchers think they were already warm-blooded and may have possessed whiskers and even a rudimentary coat of wool, giving them an edge in cold or variable climates. The Triassic was an age of trial, destruction, and rebirth. The planet was healing from the worst extinction, while new powerful lineages prepared to shape the future. Dinosaurs set out on the long road to dominance, and the ancestors of mammals quietly refined traits that would one day give rise to us. The continent was a scorching furnace under the sun of the massive supercontinent, and strange reptiles dominated both land and sea. It was a time of extraordinary transition, an evolutionary laboratory where the future rulers of Earth were forged. By the end of the Triassic, about 21 million years ago, millions of years of gradual change produced something remarkable. At last, the first true mammals appeared. These earliest forms were tiny, often no larger than modern shrews. They likely spent most of their lives hidden in darkness, active at night when the gloom shielded them from the large, dangerous reptiles that prowled the daytime world. Their small size and nocturnal habits were not random. They were vital survival strategies. By moving under cover of night and staying unseen, these early mammals avoided direct competition with the huge, formidable archosaurs that ruled the daylight hours. Small mammals did not chase the same quarry as the giant reptiles. Instead, they took up a modest niche, feeding on insects and other tiny invertebrates that the larger predators either ignored or could not grasp. Sharing the world with towering dinosaurs and fearsome hunters, these diminutive creatures were more than mere hidden shadows. They pursued their own distinct evolutionary path. Over time, they acquired traits that would later define the entire group: warm-blooded metabolism, the ability to nourish their young with milk, acute hearing, and a brain that was large relative to body size. Although these advantages did not yet make them dominant, they set the stage for the later success of mammals after the age of dinosaurs had ended. The Triassic epoch lasted until roughly 201 million years ago and was a time of continual change and fierce competition. Earth was still recovering from the most severe mass extinction, and life slowly reoccupied the empty niches. For most of that era, the land was ruled by pseudosuchians, distant relatives of modern crocodiles. They came in many shapes and sizes, and for millions of years they were the primary predators and herbivores of their time. In rivers and lakes lived huge phytosaurs, reptiles that resembled crocodiles but belonged to a different lineage. They dominated the aquatic food chains. On land, heavily armored herbivorous etosaurs roamed like living tanks. The Rauisuchians, swift and powerful hunters, prowled the continents, often larger than the early dinosaurs that shared their world. At that point, dinosaurs were still relatively small and far from becoming the planet's rulers. They had not yet risen to dominance. Instead, they survived by slipping into niches that larger reptiles left vacant. Some fed on carrion, others hunted small prey, and many were opportunistic omnivores that avoided direct competition with the big predators. Yet the stage was already being set for a sudden shift. The shift came about 201 million years ago, at the very end of the Triassic, when a new wave of mass extinction, the Triassic-Jurassic event, swept the globe. Though less catastrophic than the Permian extinction, it still delivered a massive shock. Scientists think it was triggered by a series of gigantic volcanic eruptions linked to the gradual breakup of Pangaea. These eruptions created the Central Atlantic Magmatic Province, a vast region of volcanic rock now spread across present-day North America, South America, and Africa. Enormous amounts of carbon dioxide and sulfur dioxide poured into the atmosphere, leading to rapid global warming, ocean acidification, and a cascade of environmental changes that pushed many organisms toward the brink of extinction. The groups that suffered the hardest were the dominant late Triassic reptiles: pseudosuchians, etosaurs, phytosaurs, and Rauisuchians. Many of them vanished completely,
while most dinosaurs managed to survive. The exact reason remains uncertain. Perhaps dinosaurs moved more efficiently, could consume a broader range of foods, or simply got lucky. In any case, the majority of dinosaur lineages made it through the crisis. With their main rivals gone, dinosaurs were free to grow larger, fill new ecological roles, and evolve into an astonishing variety of shapes and sizes. For a few million years after the early Jurassic extinction event, dinosaur diversity surged dramatically. Massive sauropods, valuonic herbivores as long as a bus, roamed the land alongside ferocious theropods, the ancestors of later giants such as Tyrannosaurus rex. This marked the true beginning of the age of dinosaurs.
Yet their roots lie in the Triassic, a period that was not only a time of survival, but also a pivotal turning point in life's history. It served as a testing ground where mammals, dinosaurs, and many other groups embarked on their long evolutionary journeys. Fossil discoveries from around the globe have greatly expanded our understanding of the Triassic. In Argentina's Chiguasta Formation, a fossil-rich deposit, some of the best preserved early dinosaurs have been unearthed, including specimens identified as Herrerasaurus and Iraptor. In South Africa, researchers have found fossils of ancient synapsids, among them several cynodonts, mammal relatives that illustrate the gradual shift from reptile-like creatures toward true mammals. In North America, the Chinle Formation holds a true treasure trove of Triassic reptiles, revealing in vivid detail the strange and varied world that existed alongside the first dinosaurs. Every fossil, whether a single tooth or an entire skeleton, adds a new piece to the mosaic of this remarkable era. Scientists continuously re-examine earlier data, applying fresh tools and techniques such as computed tomography and computer modeling to extract even more information. The recovery after the extinction is a striking example of life's incredible capacity to rebound, adapt, and generate novelty after Earth's greatest catastrophes. It was the dawn of new beginnings. Tiny mammals took their first steps, and dinosaurs began the long ascent to the dominance that would shape life on Earth for the next 135 million years. Imagine a world so vast and unified that one could, in theory, travel from the southern pole to the northern pole without ever crossing an ocean. This was the astonishing reality of Pangaea, a colossal supercontinent that took an incomprehensibly long time to form as the planet transitioned from the late Paleozoic to the early Mesozoic, persisting for hundreds of millions of years. It was not merely a collection of continents pressed together. Almost all of Earth's landmass was fused into a single gigantic block. The sheer size of Pangaea reshaped not only the planet's appearance, but also its entire system, especially its climate. Today, we are accustomed to a world of scattered continents and oceans, each with its own weather patterns and climate zones. In Pangaea's heyday, climate operated on a much grander scale. The supercontinent generated its own massive and harsh climate system, markedly different from today's. Coastal margins experienced milder, wetter conditions, while the interior lands were hot, dry, and relentless. Reconstructing Pangaea's climate is a challenging story of ancient weather, revealing how the position of land versus sea influences winds, precipitation, ocean currents, and even marine life. The most extreme climatic contrasts appeared deep within the continent's interior. Imagine a land so expansive that moist oceanic winds, after traveling thousands of kilometers, arrived completely depleted of moisture, dry, and unable to bring rain. In the heart of Pangaea, these arid conditions dominated, illustrating how the sheer breadth of a single landmass can shape a climate entirely unlike anything we observe today. The core of Pangaea was plagued by an unrelenting drought, far more severe than any ordinary desert. This vast arid zone stretched across what are now North America, South America, and Africa, turning the landscape into immense sand seas, ergs, where relentless winds sculpted colossal dunes. Between these dunes lay barren salt flats and occasional lakes that filled briefly after rare rains, only to evaporate quickly under the scorching sun, leaving behind thick crusts of salt and other minerals. The air was perpetually dusty, often taking on a reddish hue because fine particles of iron-rich soil oxidized in the dry atmosphere. Modern geologists have identified this ancient dryness by studying extensive layers of reddish rocks, gypsum, and rock salt strata that testify to prolonged drought and extreme heat. Surviving life in this environment required special adaptations. Early conifers and cycads developed waxy foliage that helped retain moisture and sent deep roots down to hidden water sources. The animals that inhabited the region also needed to be exceptionally resilient to cope with the chronic scarcity of water. Because Pangaea was so enormous, the interior lay far from any ocean, keeping moist air out and creating a closed, harsh climate system that covered a colossal area. In contrast, the margins of the supercontinent experienced a completely different climate. The surrounding Panthalassa Ocean and the large sea that intruded into one side of the landmass brought more temperate conditions to the coasts. The regions that would eventually become Europe, Asia, Australia, and the fringes of Gondwana received abundant moisture, regular precipitation, and milder temperature swings. Proximity to the ocean saturated the air with humidity, leading to frequent rains that nurtured lush forests, winding rivers, and extensive swamps, features that have left abundant evidence in the geological record. During the Carboniferous and Permian periods, roughly 359 to 252 million years ago, massive coal seams formed. These deposits are the remnants of gigantic tropical forests that thrived in the warm, humid lowlands along Pangaea's edges. The ground was carpeted with towering club mosses, ferns, and horsetails that soaked up rain and created dense jungles. Over time, these jungles were buried and transformed into the coal we mine today. Meanwhile, the nearby seas teemed with life. Fossils of marine creatures, coral reefs, and shell beds along ancient shorelines reveal thriving, life-rich ecosystems. Although the precise routes of ancient ocean currents are still being reconstructed, they likely carried heat and moisture inland, making coastal zones far more hospitable than the dry, dusty heart of the continent. Thus, the world of Pangaea was a realm of extremes. A barren, sun-blasted desert dominated the interior, while verdant, rain-fed lands bordered the oceans. This stark contrast underscores how the arrangement of continents influences not only maps, but also the fundamental patterns of climate and life on Earth. One of the most striking outcomes of Pangaea's immense size was the development of a gigantic seasonal weather system, a supercontinent monsoon, mirroring the modern monsoons that arise because land and sea heat up and cool down at different rates. When the supercontinent Pangaea existed, the sheer size of the land amplified a natural atmospheric effect to levels that are hard to imagine today. In the summer months, the interior of the continent warmed much faster than the surrounding oceans, making the land scorching, while the sea stayed relatively cool. This temperature contrast created a stark difference in atmospheric pressure. A low-pressure zone formed over the hot interior, while higher pressure persisted over the cooler ocean. The resulting pressure gradient drew enormous amounts of moist oceanic air towards the continent, producing monsoon rains of a scale far beyond anything we witness now. The moisture-laden winds drenched especially the coastal regions with continuous summer showers, causing rivers to burst their banks, flooding vast tracts of land, and even turning distant dry plains into lush, green landscapes for a time. When winter arrived, the situation reversed. The land cooled far more quickly than the ocean, causing the air above Pangaea to become dense and heavy. A high-pressure system settled over the continent, while the ocean retained a lower pressure. From this high-pressure area, cold, dry winds blew seaward, ushering a harsh, dry season that covered most of the supercontinent. The abrupt swing from torrential summer rains to arid winter winds left a clear imprint on the landscape, and the alternating wet and dry periods are recorded in the geological record. During the rainy seasons, rivers deposited alternating layers of coarse and fine sediments known as rhythmites, natural banding that marks the change of seasons. Ancient soils, called paleosols, also preserve evidence of the wet-dry cycle and often contain fossilized plants. Many species adapted to survive the dry months and then sprouted vigorously once the rains returned, showing how life adjusted to such extreme climate swings. Because Pangaea was so enormous, its monsoon system affected multiple regions and functioned like a planetary climate engine, far more powerful and extensive than the modern monsoons we know. Around the time the supercontinent formed, Earth experienced a major ice age often referred to as the Permo-Carboniferous glaciation. This was not a brief cold spell limited to a few areas. It enveloped the whole planet with thick ice sheets. The glaciation began more than 300 million years ago, when a large portion of the southern supercontinent Gondwana, comprising what are now Africa, South America, Antarctica, Australia, and India, slowly drifted over the South Pole. While positioned over the planet's coldest region, snowfall continued year after year without melting, even in summer, eventually building massive glaciers and ice sheets. A key factor behind this ancient glaciation was a drop in atmospheric carbon dioxide. During the Carboniferous period, vast forests grew and later died, their remains becoming buried as coal seams. This burial locked away large amounts of carbon, reducing the amount of carbon dioxide in the atmosphere and contributing to the global cooling. Reducing the amount of greenhouse gases cooled the planet and allowed glaciers to spread even farther. The expansion of ice was helped by a number of other factors. As the continents moved and began to touch each other, ocean currents changed direction. In some regions, sea passages were closed or narrowed, which reshaped the distribution of heat around the globe and permitted more ice to form at the poles. Traces of ancient glaciation are found on every southern continent. Geologists have identified tillites, rocks that consist of debris left behind by glaciers, and in many places they also discovered surfaces that have been scratched and smoothed by the slow advance of massive ice sheets. Additional clues include trough-shaped valleys carved by glaciers, dropstones, large clasts dropped by melting icebergs into fine-grained sediments, and other features that point to former glacial activity. Millions of years later, the supercontinent Pangaea drifted slowly northward. The great ice sheets began to melt, and during the Jurassic and Cretaceous periods, the Earth entered a warmer phase. This illustrates how complex and changeable Earth's climate is. Climate is governed by the motion of continents, the composition of atmospheric gases, and even the planet's orbit around the Sun. Pangaea affected not only land and ice,
but also the behavior of the oceans and the atmosphere on a global scale. Encircling Pangaea was Panthalassa, a single continuous ocean that covered most of the planet. Unlike today's oceans, which are broken into separate basins by continents, Panthalassa allowed currents to flow freely around the globe. Deep sea circulation was probably simpler and, in some regions, more stable. On the eastern side of Pangaea lay a warm, shallow sea that acted like a giant heat reservoir, playing a crucial role in temperature regulation and in exchanging water with the larger Panthalassa. The interaction of these two bodies of water generated powerful currents that have no modern counterpart. The atmosphere also behaved differently. The basic structure of atmospheric circulation, rising and sinking air cells that we now call the Hadley, Ferrel, and polar cells, was present, but the sheer size of Pangaea amplified every process. Rapid heating and cooling of such a massive land area sharpened seasonal high and low pressure zones and drove enormous monsoonal systems.
Because the supercontinent had few mountains, most of the major ranges formed later, winds faced fewer obstacles and could travel great distances with little interference. A climatic shift in one part of the supercontinent could influence regions thousands of kilometers away through a global weather link known as teleconnection. For example, a change in monsoon strength in one area could alter precipitation patterns far across the globe. Panthalassa's vast moisture stores heightened the contrast between wet coastal zones and the dry interior. The coastal margins were green and lush, while the interior was arid and often harsh, especially in winter. Pangaea's distinctive climate, scorching summers, freezing winters, fierce monsoons, and periodic ice ages, had a profound impact on life. Plants and animals in the dry interior adapted to water scarcity, whereas the rainy coasts supported thriving ecosystems with a rich variety of species. Because the oceans did not separate the land masses, organisms could disperse over long distances, but regional diversity was lower than it is today. The story of Pangaea is therefore not only a tale of a magnificent supercontinent, but also of its eventual breakup. Just as earlier supercontinents have shown, Pangaea could not last forever. Over time, it was destined to fall apart under the influence of powerful, invisible forces deep within the Earth, plate tectonics, that constantly reshapes the planet's surface. The breakup, however, was not a single cataclysmic event. It unfolded as a prolonged drama that spanned millions of years. The first fractures appeared toward the end of the Triassic, roughly 200 million years ago, and the process carried on well into the Jurassic. Initially, the changes were subtle and almost invisible. Far below the crust, pressure built up. Then the land began to rise gently, as if holding a massive breath. Eventually, the crust cracked, opening vast rifts, valleys, and deep scars across the supercontinent. Studying how and why Pangaea disintegrated helps us understand the present arrangement of continents and oceans. The ancient fractures are still recorded in rocks and landforms worldwide, like pages in the Earth's diary. From these geological clues, scientists are reconstructing the dramatic tale of lands that once formed a single, massive body before being torn apart. Why do such majestic supercontinents eventually crumble? The answer lies in the planet's inner workings.
Beneath the mantle, slow swirling currents move hot rock in enormous circles, much like water boiling in a pot. These currents drive the motion of the crust. One key concept that explains the start of continental breakup is the thermal insulation effect. Imagine Pangaea as a thick blanket covering the planet's surface. It occupied a large portion of the Earth and acted as insulation, trapping heat rising from deep within. That heat originates from the gradual decay of radioactive elements far below. Over millions of years, warmth accumulated beneath Pangaea's crust, making the underlying mantle hotter and less dense. The superheated mantle rose and pushed against the crust, causing it to bulge and stretch. Like a piece of toffee being pulled until it snaps, the crust began to tear, producing cracks and faults, early signs of the split. Another important factor was the mantle plume, a hot column of rock rising from the deepest parts of the Earth, possibly from the core mantle boundary. When a plume reached the base of the crust, it created a hotspot where volcanic activity pierced the surface. The plume supplied not only heat, but also pressure, further uplifting the crust and facilitating its breakage. A striking example of this process is the Central Atlantic Magmatic Province, often abbreviated CAMP. This massive volcanic episode occurred around 200 million years ago, right at the birth of the Atlantic Ocean. CAMP produced one of the largest known lava floods in Earth's history, covering parts of present-day North America, Africa, and Europe with millions of cubic kilometers of molten rock. The scale of that event points to one or more enormous mantle plumes that likely played a crucial role in weakening Pangaea's crust and initiating the separation of its continents. Today, the movement of tectonic plates is driven mainly by forces such as the subducting slabs that pull heavy oceanic crust down into the mantle, and by the push that creates new mid-ocean ridges, where the seafloor spreads outward. In the earliest phases of Pangaea's breakup, however, the dominant force came from deep within the Earth. Heat rising from the mantle forced the continental blocks apart from below. The first hints of rifting did not mean that oceans appeared instantly. It began with a slow, broad swelling caused by hot material pushing upward. This uplift produced high, extensive plateaus.
As the crust stretched and thinned, cracks formed, developing into networks of faults along which crustal fragments either sank or rose. The lowered blocks became long, low valleys, while the raised blocks formed higher ridges along their margins. These grabens were the initial rift valleys and the first visible signs that Pangaea was beginning to break apart. When the crust split and thinned, pressure on the underlying mantle lessened, allowing rock to melt and generate magma. The melt surged up through the cracks, triggering massive volcanic eruptions. Rivers of lava poured out, creating thick basalt flows that covered vast stretches of dark, rocky plains. Even today, ancient lava fields remain exposed, testifying to the tremendous heat that traveled from the Earth's interior to its surface and marking a major geological episode. The locations of these earliest fractures later became the birthplaces of modern oceans. A key example is the Central Atlantic Rift System, where the Atlantic Ocean first opened. The rift initiated between what is now North America and Africa, then extended southward, separating South America from Africa and forming the South Atlantic Rift System. The development was gradual. At first, the rift resembled a series of isolated, narrow valleys stretching for hundreds of kilometers. Over millions of years, those valleys linked together and widened. Remnants of ancient rift basins can still be seen today, such as the New York Supergroup in the eastern United States, where layers of river and lake sediments are interbedded with lava and volcanic ash, recording the splitting of the land. A comparable process occurred farther south, gradually pulling South America away from Africa. Scientists point to the East African Rift System as a modern analog. Africa is currently being divided into two halves. In East Africa, one can observe broad, uplifted regions, deep faults that form grabens and horsts, chains of active volcanoes, and long lakes that fill the rift valleys.
This living laboratory demonstrates that the same forces that once tore Pangaea apart are still at work. Not every rift evolves into an ocean. Some begin to split the continent but never reach completion. These are known as failed rifts or alacogens. They are the forgotten scars on the crust, places where land started to break apart but did not fully separate. Over time, thick sediment blankets often accumulate in these zones, and new tectonic stresses can reactivate them.
Some failed rifts continue to play important roles. For instance, in the Pangaea region of West Africa lies a failed branch of the South Atlantic Rift. In the heart of the United States, the reef trial food area marks the leftover of a broken-off piece that once belonged to the ancient ocean Iapetus, a sea that existed long before the supercontinent Pangaea. These ancient rifts act like time capsules. They keep the Earth's old layers intact and often hide valuable oil and natural gas reserves. The breakup of Pangaea left its record all over the planet, and geologists are busy studying the clues in many different geological settings. Some of the most obvious signs are found in the deep cracks and valleys that opened up when the continents began to pull apart. As the crust stretched, rift valleys sank, forming broad basins that later filled with silt, sand, gravel, and whole systems of rivers and lakes. Over the ages, sediment piled up in these valleys, and the rain and river waters left behind conglomerates made of ancient material that had settled in water. A frequent feature of those deposits is a reddish hue. The red color comes from iron-rich minerals that oxidized when exposed to air. This color tells us that the climate at the time was often hot and dry, much like today's deserts. In partly closed rift valleys where seawater sometimes entered and then evaporated, thick layers of evaporites formed. These include halite, the rock salt we know, and gypsum, a soft mineral used for plaster. The salt layers grew through repeated cycles of flooding and drying, as if a shallow pond kept evaporating under the sun. Those evaporite sequences are not just curiosities, they are crucial for oil and gas exploration because they can trap valuable hydrocarbons beneath them. When the climate was wetter, or during rainier periods in Earth's history, the low-lying parts of the rift system nurtured swamps and lush vegetation. Over time, those marshy areas turned into coal seams, showing that not every rift valley was a barren, dusty plain. Some were green and teeming with life. Perhaps the most striking evidence of Pangaea's disintegration comes from the igneous rocks that rose from deep magma. As the crust stretched, the mantle thinned and molten rock poured out in massive lava streams. This produced extensive fields of dark volcanic basalt that cover huge regions. Famous examples include the Parana Basin in South America and the Karoo Province in southern Africa. Some of those lava flows were so thick that when they cooled, they cracked into striking hexagonal columns, a pattern known as columnar jointing. Lava didn't stay only on the surface. Magma forced its way into cracks underground, spreading both vertically and horizontally to form dikes, vertical sheets, and sills, horizontal sheets. These frozen channels resemble a plumbing system inside the rift zone. By analyzing the chemistry of the volcanic rocks, scientists can pinpoint the magma's source, often deep in the mantle, and understand how the stretching of the crust drew the melt upward. At the structural level, the clearest sign of rifting is the presence of normal faults, breaks in the crust where one side drops down as the crust pulls apart. These faults appear on geological maps and become even clearer when explored with seismic waves that reveal the Earth's interior. Research also highlights classic graben and horst structures, lowered blocks flanked by raised blocks, which develop as the crust stretches and fractures. In many regions, ancient rift valleys lie concealed beneath thousands of meters of younger sediment. Various physical techniques, gravity surveys, seismic reflections, and the like still enable us to recognize the thinned crust. An equally intriguing line of evidence comes from paleomagnetism, the study of Earth's ancient magnetic field. When volcanic rock cools, the magnetic minerals it contains become locked in the direction of the magnetic field that existed at that moment. By examining such magnetic signatures in rift zones, geologists can determine when the rifting began and how fast the continents have drifted. As a rift evolves into an expanding ocean floor, the magnetic record is preserved as symmetrical stripes on either side of a mid-ocean ridge. Like a barcode, these stripes allow precise dating of the ocean's opening and the continent's divergence. Fossils also tell the tale of Pangaea's breakup. Though they do not record rifting directly, they provide strong indirect clues. For instance, fossils of the small, pig-sized reptile Lithospheric have been found in Africa, Antarctica, and India, regions that today lie on opposite sides of vast oceans. This indicates that those lands were once joined together in the massive supercontinent Pangaea. After the continents separated, the species followed independent evolutionary paths, creating a biological timeline that mirrors the geological one. Eventually, rifting reaches its final stage. The continental crust tears completely, and mantle magma not only intrudes through cracks, but also creates new oceanic crust. This is how a new ocean begins to form. A striking modern example is the Red Sea, a long, narrow waterway between Africa and the Arabian Peninsula. It is a contemporary rift zone where the crust is stretching and new seafloor is being generated, much like what occurred at the onset of Pangaea's disintegration. The decay of Pangaea stands as one of the most powerful and gradual transformations in Earth's history. It did not happen in an instant. It unfolded over millions upon millions of years. The process started with the stretching and cracking of the crust, the emergence of rivers and lakes in the lowered valleys, massive lava flows, and the slow accumulation of thick deposits of salt and coal. It was an era of tension, fire, and change. Today, evidence of this ancient drama is visible everywhere, in fractured rocks, fault lines, volcanic scars, and matching fossils on opposite sides of the oceans. These geological traces are the imprints of the slow and dramatic breakup of Pangaea, reminding us that the planet's surface never stays still. The continents continue to drift, split, and occasionally reunite in an endless cycle. The moving Earth retains the memory of Pangaea deep within its layers. Imagine the Earth not as a motionless, silent stone, but as a living, breathing giant with a fiery heart and restless spirit. Far beneath our feet, mighty forces are constantly at work, reshaping the surface above. For hundreds of millions of years, continents have drifted like slow-moving pieces of a mosaic. Sometimes they collide, forming massive supercontinents such as Pangaea. Other times they fragment spectacularly, giving rise to new oceans and forever altering the planet's visage. What immense power can cause something so massive and solid to move, split, and change so dramatically? Many scientists believe the answer lies hidden beneath the surface, an unseen engine that subtly guides the destiny of entire continents. Deep beneath the Earth's surface lie towering, fiery structures known as mantle plumes and hotspots. These are not accidental quirks of the planet. They act like internal furnaces that draw massive amounts of heat upward, offering vital clues about how the Earth has moved for millions of years. To grasp these hidden forces, we must venture far below the crust, where mountains stand and rivers carve, into a realm that is anything but calm. Below the solid crust and above the molten outer core spreads a vast layer called the mantle. It stretches for thousands of kilometers and, over enormous time spans, behaves more like a thick, viscous liquid than a rigid rock. The mantle slowly circulates through convection. Picture a giant pot of soup simmering on a stove. The hot material rises from the bottom while cooler material near the surface sinks. In the mantle, this same continuous mixing occurs, but instead of minutes, it takes millions of years. Mantle plumes appear as massive columns of unusually hot rock that pierce straight through this sluggish material. Many geologists think a plume begins its tense at a mysterious boundary deep inside the planet, where the mantle meets the outer core. This hidden zone lies roughly 3,000 kilometers beneath our feet and is known as the D-prime layer. Temperatures there are astonishingly high, comparable to the surface of the sun. In that scorching region, portions of the mantle become so heated that they start to rise, much like a hot air balloon lifting off because the warmed air inside is lighter than the cooler air outside. The overheated rock becomes slightly less dense than the surrounding mantle and begins a long, gradual climb toward the surface. The ascent is not chaotic. It follows a strikingly orderly pattern. A typical plume resembles a mushroom, a slender, elongated stem that stretches from the deep interior, topped by a broad, rounded head. This head can spread hundreds, even more than 1,000 kilometers across, lying just beneath the Earth's outer shell, the lithosphere, which includes the crust and the upper mantle. When the plume reaches the base of this rigid layer, it starts to cause major changes. First, the heat and pressure from the plume push up the lithosphere, much like a hand pressing down on a soft carpet. This creates a bulge or dome on the surface that may rise several hundred meters or even exceed 1 kilometer in height. The uplift stretches the overlying rock, making it thinner and more fragile, akin to an overstretched rubber band. Eventually, this stretched rock cracks, forming deep, narrow rift valleys where the Earth appears to be torn apart. But the story does not end there. The intense heat of the plume melts part of the mantle rock directly beneath the stretched crust, generating huge volumes of magma, molten stone that is lighter than the solid rock around it. This magma exploits cracks and faults in the lithosphere, rising to the surface and triggering massive volcanic eruptions. These eruptions are not ordinary volcanoes. They are colossal events, capable of flooding entire regions with lava. Geologists refer to such extensive volcanic formations as large igneous provinces. In the distant past, some of these lava flows covered areas the size of whole countries. Notable examples include the Deccan Traps in present-day India and the Siberian Traps in Russia, both linked to ancient activity of mantle plumes. These structures are built from massive layers of solidified lava that stand as a mute testimony to the tremendous forces deep inside the Earth. The whole sequence begins when intense heat from below pushes the surface upward, causing it to bulge, crack, erupt, and eventually split apart. No metaphor, just real geology. And it is the key driver of continental breakup. Rising mantle plumes weaken the crust from underneath. As the magma ascends, it creates slopes that gravity can act upon. The crust thins and breaks more easily. Flowing lava further softens and lifts the land, and eventually the whole region may fracture widely, sometimes giving rise to a new ocean. The two halves of a continent drift apart, and an oceanic basin forms between them. A classic illustration of this process is the disintegration of the ancient supercontinent Pangaea.
Picture it as a single giant landmass that once joined almost all of Earth's continents. Scientists think that about 200 million years ago, powerful internal tides produced mantle plumes beneath Pangaea. These plumes caused the surface to rise dramatically and triggered massive volcanic eruptions. The resulting flood of lava built a huge volcanic plateau. The internal heat and activity weakened Pangaea's thick crust, making it vulnerable to stretching and compressional tectonic forces. In the end, the combined internal and external thermal stresses exceeded the strength of the crust. Cracks opened, the continents began to separate, and the once unified Pangaea broke into the smaller continents we recognize today. Fire deep within the Earth helped tear apart the supercontinent and continues to shape our planet.
Hotspots are surface expressions of far deeper, more dramatic processes beneath our feet. When a superheated plume rises from the mantle and melts the rock above the rigid lithospheric layer, it creates a long-lasting source of volcanic activity. Many hotspots, such as the well-known one beneath the Hawaiian Islands, stay roughly stationary in the mantle while the Earth's surface, carried by moving tectonic plates, slides over them. As the plate moves over a fixed hotspot, repeated eruptions burn new volcanic islands, leaving a trail of older islands behind, much like a conveyor belt passing over a stationary lamp that leaves scorch marks on the moving belt. These volcanic chains give scientists valuable clues not only about the origins of volcanoes, but also about the motion of tectonic plates over millions of years. There is strong evidence that mantle plumes originate from deep within the Earth, far below the shallow regions where most volcanic activity occurs. Volcanism helps us decipher plate movements by the scale, style, and location of eruptions. Occasionally, enormous eruptions cover vast areas with lava in just a few million years, a geologic instant. Such events are called basaltic flood eruptions, and they are linked to large-scale tectonic processes. Slow lava drifts along the middle of ocean ridges, while in subduction zones it can erupt explosively from cone-shaped volcanoes. The extensive basalt sheets that cover these areas point to an extraordinary process hidden beneath the crust, a massive surge of heat and magma rising straight from the mantle. The chemistry of the lava tells the story of its birth. Most of these flows belong to tholeiitic basalts, which form when deep mantle rock melts, even though the melting takes place relatively close to the crust. This chemical signature lets scientists tell apart deep-sourced mantle plumes from volcanism that results from stretching of the continental crust, the latter usually producing silica-rich lava. One of the strongest clues is where the biggest eruptions happen. When they occur far from the edges of tectonic plates, right in the heart of a continent, they strongly suggest the influence of a mantle plume. The majority of volcanoes sit along plate boundaries where plates collide, pull apart, or slide past each other. Therefore, volcanic activity that appears in the interior of a plate often means a hot plume from deep within the Earth has pierced the surface, lifted the crust, and begun to split it. That is exactly what took place during the early breakup of Pangaea, the ancient supercontinent that once held together most of the planet's land. Around 200 million years ago, enormous volumes of lava spilled over the regions that would later become North America, South America, Africa, and Europe. These lava floods acted like a warning sign as Pangaea started to burst apart under internal pressure. The sequence usually follows a predictable pattern. First, the head of a mantle plume pushes against the lithosphere, causing the crust to bulge and stretch, forming rift valleys that turn into deep cracks or trenches. When the plume head is exhausted, huge amounts of magma are released, spreading across the surface as flood basalts. This intense fire marks a point of no return. The weakened crust eventually splits, paving the way for the birth of new oceans. Often this volcanic episode comes just before the onset of ocean floor spreading, serving as a fiery overture to the planet's dramatic reconfiguration. A perfect illustration of this process is the Central Atlantic Magmatic Province, or CAMP. About 200 million years ago, a massive outpouring of lava ran along the seams where Pangaea was preparing to divide. The timing and location were no coincidence. They reveal a direct link between large-scale volcanism and the forces that opened the Atlantic Ocean. It was as if the Earth sounded a loud alarm, heralding a tectonic upheaval that would reshape its surface for millions of years. Even after the continents split, mantle plumes and hotspots keep working. Moving tectonic plates leave behind striking chains of volcanic islands, such as those that form the Hawaiian archipelago. These island chains are more than beautiful scenery. They are natural maps that record the direction and speed of plate movement over vast periods. Each island or seamount acts as a marker, a piece of a mosaic that tells the story of how Earth's plates have shifted. The saga of mantle plumes and hotspots is a tale of immense power rising from the depths, delivering heat and molten rock to the planet's outer shell. That energy can lift land, stretch it, and eventually tear it apart. The massive volcanic eruptions that poured out, especially the creation of huge igneous provinces, clearly signal a profound shift in the Earth's surface. These events are neither random nor ordinary. They read like a warning from the planet itself, suggesting that the supercontinent, much like Pangaea, was under intense stress and poised to break apart, giving rise to new oceans and a fresh chapter in the planet's ever-changing story. Picture the distant past, hundreds of millions of years ago, when almost every piece of land on Earth was joined together in a single, enormous continent. This was Pangaea, a colossal landmass stretching from the frozen southern pole to the icy north. It was a world of ancient deserts, scorched by a relentless sun, towering mountain ranges that have long since been worn away, and silent, sky-piercing monuments that testified to the epic collisions of continents that forged this massive expanse. A large portion of Earth's deep history, life on land and in the seas, unfolded in a world where the separation of continents seemed, for a time, to have halted. The crust appeared stable and the continents were locked together in an ancient, strange unity. Yet beneath the surface, powerful forces were gathering unnoticed. Even the greatest structures are not eternal, and no matter how massive Pangaea was, it was destined to split. Its slow and dramatic decay became one of the most extraordinary geological events in the planet's record. It did not happen in an instant. It was a long, chaotic, and fiery process. The first major episode in this story was the birth of the Atlantic Ocean, which began with one of the planet's largest volcanic events, a massive igneous province often called a large volcanic province or large igneous province. Before we explore that fiery episode, let's first understand how Pangaea came into being. Pangaea did not appear all at once. Over dozens of millions of years, ancient continental fragments collided and merged, gradually assembling the supercontinent. About 300 million years ago, these collisions united almost the entire land surface of Earth into a single, immense continent. The formation of Pangaea profoundly altered climate, ocean current patterns, and the trajectory of evolution itself. Beneath its massive, sprawling surface, powerful forces were at work. Deep inside the Earth, heat rose from the mantle, generating slow, thick currents like a dense soup simmering in a pot. These currents accumulated beneath Pangaea's crust, placing the land above under increasing pressure. The first signs of impending change were subtle. Pangaea did not explode or collapse suddenly.
Instead, it began to stretch so gradually that a human refinement would be unable to notice. In the early stage, known as continental rifting, the crust behaved like a thick piece of dough being pulled apart. First, it lengthened, then it thinned in the middle, and finally it fractured. As the continental crust of Pangaea stretched, cracks and sunken valleys, rifts, grabens, and half-grabens formed, creating a mosaic of blocks of land separated by faults. These elongated depressions eventually became narrow basins destined to develop into the earliest portions of the Atlantic Ocean. Rivers flowed into the deepening fissures, carrying silt, sand, and other sediments. Layer by layer, this material built up, leaving a detailed geological record of the dramatic era. Then came the true geological spectacle, a gigantic, fiery event that accelerated the slow, full-scale rifting of Pangaea's breakup. This eruption gave rise to a massive volcanic province, marking the moment when the continent's gradual division transformed into a spectacular and violent geological transformation. It wasn't a typical volcanic event. It was one of the biggest lava outpourings ever recorded on the planet. The disaster happened about 200 million years ago, right at the transition from the Triassic to the Jurassic epochs. The region known as the Camp is among the largest igneous provinces on Earth, covering a vast expanse of solidified volcanic rock. Its eruption was not accidental. It lined up almost exactly with the start of the breakup of Pangaea and the birth of the Atlantic Ocean. Imagining the size of the eruption is difficult. Lava spread over the areas that today form North America, South America, Northwest Africa, and Southwest Africa, as well as Europe, 4 continents that at the time were still fused into Pangaea. Scientists estimate that the total volume of magma released during the camp activity lies between 2 and 4 million cubic kilometers. That amount of lava would be enough to bury whole countries under several hundred meters of hard rock. For comparison, think of the eruption of Mount Tambora in 1815, the largest eruption recorded in human history. Now, multiply that scale by thousands, perhaps even tens of thousands.
That was the primordial power we are dealing with. The eruptions did not come from tall, cone-shaped volcanoes like the ones we see in movies. They were effusive. The lava streamed out in broad sheets, flooding the landscape and forming thick, dark, basaltic layers. Within the camp lava, researchers have identified a special volcanic rock called toe basalt, which forms when deep mantle material melts and rises to the surface. This shows that the camp eruptions were not a shallow phenomenon. They originated deep in the earth, likely driven by a massive mantle plume, a giant column of hot rock that rises from great depths and melts everything in its path. When the plume reached the base of Pangaea's crust, it caused widespread melting, pushed magma upward, and eventually produced an enormous flood of lava. Most of the camp lava was emitted over a relatively short span in geological terms, perhaps only 1 to 5 million years. This intense activity coincided with the very beginning of the Atlantic opening, so the camp event did not merely occur alongside the disintegration of Pangaea, it helped trigger it. The heat and pressure from the plume weakened the already stretched and thinned crust, much like a cracked sheet of glass being heated. Eventually, the crust gave way, the Earth split, and a new ocean, the modern Atlantic, was born in the rift. One could say the planet reached its tensile limit, and the deep fire burst forth in a grand release, tearing the crust apart and ending the era of a single supercontinent. From that moment on, the lone supercontinent vanished, replaced by the world of drifting continents and vast oceans we know today, forever shaped by forces that once split the greatest massif in Earth's history.
To truly grasp the origin of the Atlantic Ocean, imagine first a proto-ocean. It was not the wide, deep ocean we see on modern maps. Rather, the early Atlantic resembled a barely formed sea, long and narrow, like a giant crack in the Earth's crust. In its center, a completely new oceanic crust was generated from melt that rose from the deep mantle. As the molten rock cooled and solidified, it built the ocean floor while the ocean continued to expand. When the continents started pulling apart, the thick crust beneath them cracked open. Hot mantle rose through the gap, melted because the pressure dropped, and solidified into fresh crust right along the center of the opening. That is how a new ocean is created.
At first, the early Atlantic, sometimes called the Proto-Atlantic, was a long, narrow strip of water lying above hot crust, with fierce volcanic activity steaming along its middle. The Atlantic Ocean did not appear all at once. It grew slowly, first in the middle and then spreading northward and southward. One of the earliest clues of this great event was the massive eruption of the Camp Province. A huge zone of volcanism marked the first big rift between what would become North America on one side and Africa with South America on the other. As the rift widened, the ocean floor kept expanding. Along the growing crack, now known as the Mid-Atlantic Ridge, new oceanic crust was constantly added. The ridge is a vast underwater mountain chain that runs along the spine of the Atlantic and is still active today, constantly forming new seafloor and pushing the continents apart. Geologists have gathered a wealth of evidence for this process. The clearest sign comes from magnetic stripes in the oceanic crust. When new crust forms at the center, it records the direction of Earth's magnetic field at that moment. Over millions of years, the magnetic field has flipped many times, so the seafloor shows alternating bands of normal and reversed magnetization. Like a barcode, the pattern is mirrored on both sides of the Mid-Atlantic Ridge. These stripes tell exactly how, when, and where the ocean floor was created and help us reconstruct the history of the ocean's growth. Additional clues come from the shape of the seabed, especially the rift valleys where the crust is being torn apart, and from marine sediments that change from shallow water types to deep sea deposits, showing how the basin deepened as the proto-ocean expanded. The birth of the Atlantic was not only a geological event, it also had huge effects on climate and life. The Camp eruption about 200 million years ago spewed enormous amounts of volcanic gases, mainly carbon dioxide and sulfur dioxide, into the atmosphere. Carbon dioxide caused global warming and made the oceans more acidic, hurting marine organisms. Sulfur dioxide, on the other hand, briefly cooled the planet because volcanic aerosols blocked sunlight. After this short cold snap, the world probably became even hotter than before. Many scientists think that this dramatic environmental turmoil contributed to the Jurassic-Triassic extinction, one of the 5 major mass extinction events in Earth's history. The exact chain of events is still debated, but the timing matches well. Ecosystems were already fragile, and such giant eruptions could have delivered the final blow that wiped out many species. In that sense, the beginning of the Atlantic also marked the end of the Old World. As the Proto-Atlantic expanded, it began to reshape the planet in other ways. Before the split, all the oceans formed a single global sea that surrounded the supercontinent Pangaea. The emergence of a new ocean disrupted the old system of currents and set the stage for the modern oceanic world. New ocean currents emerged, carrying warm water and reshaping the global climate in fresh ways. These currents forged new coastlines and created entirely novel habitats for marine life to evolve. As continents continued to drift apart, their plants and animals adapted differently, giving rise to the remarkable diversity we observe today across the world's land masses.
Yet the story does not end there. The Mid-Atlantic Ridge remains active, constantly generating fresh ocean floor as North America, South America, Europe, and Africa pull away from one another. The Atlantic Ocean rises only a few centimeters each year, but over millions of years those tiny increments accumulate. The immense forces that split the ancient supercontinent and birthed the ocean are still at work, slowly but surely molding our planet. Consequently, the early Atlantic was far more than a simple crack in the earth or a narrow strip of water marking the decay of a great supercontinent. It was not merely a volcanic episode, but a fiery proclamation that the world was undergoing a permanent transformation. This episode in Earth's history demonstrates that deep-seated forces, volcanic eruptions, and gradual continental drift are all chapters of a single, long-running narrative. Proto-Atlantic became a dramatic and often violent arena where nature reshaped the planet's surface and began to carve the map we now recognize. This marked the final chapter of Pangaea's existence and the opening act of the Atlantic Ocean's history, a story still being written beneath our feet. Before this, as the mighty Pangaea began its slow and dramatic breakup deep within the Earth's crust around 250 million years ago, the planet's landmass looked and felt completely different from today. Imagine a single enormous continent stretching almost from the northern pole to the southern pole, a colossal mosaic of Earth's crust.
Unlike today, oceans did not split this land into separate continents. The continent was largely dry, dominated by a harsh continental climate, especially far inland. The interior resembled a desert, with scorching summers giving way to bitterly cold winters. Coastal regions, though extensive, were milder, wetter, and more temperate. Because the land was not divided by vast oceans, animals and plants could roam across immense distances. Dinosaurs, small wool-covered cynodonts, early mammal relatives, and robust plants could move freely and populate the entire supercontinent. The lack of large seas meant that the mixing of animal species and the spread of plants were unimpeded, so life in different parts of Pangaea was strikingly similar. Physically, the planet remained massive, but biologically, it was tightly connected. For terrestrial flora and fauna, the world seemed smaller and more unified, resulting in fewer regional differences than we see today. Beneath this seemingly tranquil surface, powerful forces were already at work deep inside the Earth. The mantle beneath the crust slowly shifted under the influence of heat rising from the planet's core. These movements caused the Great Pangaea to stretch, crack, and eventually fragment. This did not happen overnight. The process unfolded over tens of millions of years. The first signs of profound change appeared as massive fissures in the land, rift valleys that resembled today's East African rift, but on a far grander scale. Deep beneath the Earth's crust, molten rock forced its way upward, spilling out as lava and laying down extensive stretches of dark volcanic stone. These basaltic eruptions reshaped the terrain and even left their mark on the atmosphere. At this stage, the rift valleys had not yet filled with seas, but they already formed solid physical barriers. Where the rifts met the surrounding land, towering mountains and deep valleys rose, making it hard for creatures to move from one side to the other. Over many ages, the rifts widened and sank until they dropped below sea level. Then, the waters of the Great Panthalassa, the massive ocean that surrounded Pangaea, began to creep inward. Shallow seas slowly covered the low-lying areas, carving narrow yet important water corridors through what had been continuous land. For terrestrial animals, these corridors acted like vast oceans. isolating populations that could neither fly nor swim for long periods. Wind found it tougher to carry seeds across, and even birds or insects sometimes failed to bridge the gaps. Thus, the continent was split not only by geography, but also by biology. This growing isolation sparked one of evolution's chief drivers: divergent development. When a group of plants or animals becomes divided and can no longer interbreed, each part starts to change along its own path. Gene flow stops, each side adapts to its own conditions, and its form, behavior, and traits evolve independently. As this divergence continued, some land masses drifted toward the equator, becoming hot and wet, while others moved toward the poles, growing cold and dry. Every new continent acquired its own climate, vegetation, predators, and challenges. Plants felt the impact especially strongly. While Pangaea supported a broad suite of species adapted to a single, expansive climate, the breakup created fresh environments. Some regions received abundant rain, others turned arid. Soils varied from one area to the next. A wave of new plant life appeared, each group tuned to its local setting. And around this time, flowering plants, angiosperms, began to thrive. Depending on where they grew, they invented novel ways to lure pollinators, such as insects and birds, and to spread their seeds. Picture a fern that once carpeted the whole supercontinent. After a new sea sliced its range, one branch adjusted to dry soils, while the other pursued rapid growth in humid tropical forests. After countless generations, they would become distinct species, even though their ancestors looked alike at first. Animals underwent even more dramatic shifts. Early mammals during the Pangaea era were small, mostly nocturnal, and lived in the shadows of dinosaurs. When the continents split, mammalian lineages followed separate evolutionary routes. A classic example is the division between marsupials and placental mammals. Marsupials, like the kangaroo, could give birth to tiny young that finished developing inside a pouch, and they spread widely across the southern continents of Gondwana, which later gave rise to Australia and South America. Placental mammals, whose offspring developed longer inside the mother, came to dominate the northern continents of Laurasia, including North America, Europe, and Asia. The rising seas kept these groups apart for tens of millions of years, and their independent evolution produced the astonishing diversity of modern mammals we see today. Even the dinosaurs, who dominated the Mesozoic era, felt the slow pull of decay. During the Triassic and early Jurassic, dinosaurs worldwide were much alike, but as rifts widened and oceans formed in isolation, different lineages began to change. Giant long-necked sauropods and heavily armored stegosaurs, for instance, branched out, adjusting to the distinct conditions of their continents. On the southern land masses, a group of enormous sauropods known as titanosaurs spread widely. These titanic herbivores took on many shapes and sizes, evolving along paths different from their northern cousins. Separated by great distances and seas, each group developed its own traits and survival strategies, shaped by the surrounding flora and predators. The transformations did not spare only the well-known megafauna. They also touched tiny insects, amphibians, and freshwater fish. Rivers that once freely crossed Pangaea broke apart, and fish that had lived in a single water system suddenly found themselves in wholly new environments, eventually giving rise to new species. Amphibians that relied on moist habitats suffered as the arid interior of the supercontinent grew and new oceans blocked their routes for recolonization, leading to distinct amphibian forms appearing on each isolated continent. These biological shifts were tightly linked to major climatic changes. The drifting continents altered ocean currents and wind patterns. The once vast panthalassa became more intricate as new seas such as the Atlantic and Indian emerged. The movement of warm and cold water reshaped the planet's climate, creating fresh climatic zones. Some regions grew wetter and were covered by tropical forests, while others dried out and turned into deserts, and many places experienced sharper seasonal swings. Plants and animals had to learn to endure prolonged droughts, frigid winters, and scorching summers. Volcanic activity along the rifts released greenhouse gases that warmed the world, while the newly formed oceans later absorbed carbon dioxide, helping to cool the climate again.